Okay, good morning, everyone. I hope you've had a nice evening yesterday. So here you can see like the program of the day. So as usual, we'll start with an oral session and sponsor events. Then the break, poster session, lunch break, our keynote speaker. Today is Karim Lecadier. Then another oral session on foundation models. Then the last poster session of the day. So here it will really be critical for everybody to take down their poster at the end of that session. I mean, we need basically to finish the day on time, so please do not forget to take down your poster. For the ones who had their poster yesterday, you can find them at the registration desk. So please, at the end of this morning session, go pick up your poster if you haven't done it yet. At the end of the day, we'll have an oral session dedicated to papers accepted at Melba, and then we'll have the awards and closing. I think that's all what I needed to tell you this morning. So let's start with the oral session 3.1 on explainable AI and uncertainty.
Hi. Okay, great. So welcome everyone to this session on explainability and interpretability. So my name is Benjamin Billot. I'm a postdoc at MIT.
Hi, my name is Jonas Riccardi. I'm at Lausanne University Hospital in Switzerland, and it's great to see actually not quite a few of you after last night, so it's fantastic. So let's start right away with the first talk, spatial temporal encoding of brain dynamics with surface masked autoencoders, presented by Simon Dahan.
Good morning, everyone. Thank you for joining this early session. And thank you for joining this presentation on spatial temporal encoding of brain dynamics with surface masked autoencoders. So yesterday, during the geometric deep learning session, I had the chance to introduce the MSSIT, which was a method to extend surface vision transformers for dense prediction tasks. So today we're going to continue to talk about surface vision transformers, but in a very different paradigm, related more to self-supervision and how we can leverage large-scale data sets in neuroimaging. So understanding brain anatomy and dynamics of brain activity requires models that generalize across individuals and populations. However, as we all know, neuroimaging datasets are usually relatively small. So for many reasons, first is that some neurological conditions and disorders are quite rare. And another reason is that acquiring high-resolution images can be really hard. So even if we take the HCP datasets, we only have about 1,000 subjects, which is great, of course, but it's quite limited for some applications. Some other large-scale datasets exist. For instance, the UK Biobank, with maybe not as high-resolution images as the HCP, but with a lot more subjects, so hundreds of thousands. And the question is now how to leverage medium and large datasets with deep learning in order to learn very interesting information about the brain and to use them for smaller datasets. So obviously, one of the solutions would be to use self-supervision to learn robust and generalizable representations. So as we saw yesterday, the surface vision transformer, or SIT, is a strong backbone for surface deep learning. It learns long-range dependencies across the cortex using self-attention between surface patches. However, of course, there are limitations, and one of the limitations is the lack of inductive biases in the architecture, which is inherent to the transformer architecture, which makes it, for some applications, quite data-hungry, so need a lot of data to be able to perform, and prone to overfitting and poor generalization in some specific small data regimes. Of course, the lack of inductive biases in transformers is not new. It's something that happens in computer vision or in natural language processing with transformer architectures. And one of the solutions has been to pre-train a pre-training strategy on very large data sets. Particularly, autoencoder approaches have been used, and those approaches try to reconstruct corrupted inputs. One of the most famous one is the mask autoencoders, which was introduced in 2021 and works as an image denoising approach by masking a high portion of an input image that you can see on the left. Use only the patches that were not masked in an encoder, a transformer encoder, and then use the latest representation of those patches to try to predict the rest of the image that was masked. So pre-training surface deep learning models on large datasets could help us in 3 different ways. First, to improve the generalization capabilities of transformer-based architectures, to learn strong cortical representations from large neuroimaging datasets, and to transfer the knowledge from large to small datasets. So here we are introducing 2 methodologies, the surface mask autoencoder, SMAE, and the video surface mask autoencoder, VSMAE, for multivariate and spatiotemporal pre-training of cortical signals over regular icosahedral grids. So let's dive into the architecture. So as yesterday, it starts always the same. So we have a native mesh that we project on the sphere, and we partition thanks to an icosahedral grid of lower resolution. From a very high level perspective, so the surface mask autoencoder works by masking part of the input sphere, so masking some of the tokens from the input sphere, processing that information, and then thanks to the decoding part, we try to predict the missing patches that were masked, and to obtain a reconstruction, and then we compute a loss between the inputs and the reconstruction. So this is the surface mask autoencoder from a high-level perspective. So in short, it learns to reconstruct masked tokens that were masked between 50% and 90% of the entire sphere from the set of unmasked tokens. And this framework integrates the surface vision transformer for the encoder and the decoder part. So a few comments about the architecture. So there are a few interesting points to note. So first, this is a very efficient framework with most of the weights that are actually put for the encoder part. It's an asymmetric encoder-decoder architecture with the encoder having a bit more layers than the decoder. The reason is that the encoder is processing less information because it's only processing the masked token. So the sequence is reduced. For instance, if you are masking your surface with 90%, you only have 10% of the patches that are processed by the encoder, so you can make it deeper. The decoder is processing the entire sequence, so and therefore is reduced in terms of the number of layers, but making it this way asymmetric, the framework for supervision is very efficient. If to describe a bit more what's happened for the masking, so let's say that we have a first initial sequence of triangular patches with positional embeddings. Then at random, we obtain a set of masked tokens, and we use this mask to only extract an unmasked surface. And this unmasked surface, will be processed by the encoder and obtain a latent representation of that unmasked surface. Then, with this unmasked representation, there is the unmasking part, which is essentially works by appending what we call mask embeddings, which are essentially random embeddings. We have an unshuffling operation that puts the order of the original sequence. So in yellow, you see the mask embeddings, the random tokens that were masked. And in blue, you see the latent representation from the unmasked tokens. We unshuffle so that we try to predict the real values of the yellow tokens in the sequence, the patches that were masked. Okay, sorry for the formatting, but a few results in terms of reconstruction. So here I'm trying to reconstruct circle depth at different ratios. So on the left, you have one subject from the test set that's going to be masked at different ratios. So you have 25% to 90% of the surface that is masked. And on the right, you will have the reconstruction of those surfaces using the self-supervision approach I just described. So you can see, of course, that it's doing quite a great job actually on reconstructing the surface. You can see some subtle differences between the different ratios. The more you mask, the more general the reconstruction will be in terms of capturing population level information, and the less you are masking, the more subject specific it will be. Actually, a more quantitative analysis gives us this result that the 50% and the 75% masking ratio yields to the strongest visual reconstruction in terms of reconstruction and also performance on downstream tasks. In the following, I will mostly use the 50% masking ratio. So this was this framework I just showed you was made for static images. So, for instance, circle depth, as I was saying. But there is also a version of the mask autoencoder that works for videos. So instead of masking an image in space only, you can mask an image, a set of frames in space and time. And there are multiple strategies for that, notably the agnostic space-time masking or the tube masking strategies that exist in the literature. In the case of medical imaging, the thing that could be related to videos would be functional MRI. Unfortunately, there are still differences between fMRI frames and videos. First, it's way less structured. It's way more noisy. fMRI frames are way more noisy than videos. And also there is far less temporal redundancy between frames, as for instance, in the video frames, if you extract two successive video frames, they will be very similar. But for fMRI, it can be very different, especially for task fMRI. So here we are turning the SMAE I was just showing you to a VSMAE, a video surface mask autoencoder, by adapting a few things for processing fMRI signals. So we reduce the masking ratio to 50%, as using higher masking ratio leads to smaller resolution outputs and results. And we replaced the masking strategy that were present in the literature for video mask autoencoder with a spatial temporal masking by concatenating frames and masking them in space and time. And we used the 7 Tesla HCP dataset for the movie watching experiments, so people watching movies and an fMRI for a few hours. And we use frames from that dataset. So actually, it's a very small modification from the previous framework. Instead of having a single input surface, you have a set of surface in space and time. Once the patches are extracted for all those frames, T0, T0 plus 1, T0 plus 2, you concatenate them and then you mask them in the same way that was done for the static version. You mask the frames in space and time, and then you process this information and you try to reconstruct the signal as output. So here I'm showing an example for 3 frames, but actually you can go on a single GPU with 24 gigabytes of RAM of memory. Sorry, you can go to 8 frames easily. And this is some of the reconstruction results. So here, each row is representing 1 frame. The frames are all consecutive in this fMRI recording. This is the masking, and this is the reconstruction. So important points here is that the general spatial temporal patterns of brain encoding seems to be captured by the framework. Another example is shown here, but I have more examples if you're interested that I can show you for the oral session. But once all this self-supervision is done, now actually the interesting part is to extract the SMAE encoder that was pre-trained and use it for later tasks. So we can use it in 2 ways. First, we can use it for downstream tasks, so retraining it on specific tasks to improve the performance, or we could use it to transfer learning between a large and a small data set. So for the first approach, so improving the fine-tuning approach. So here I'm showing some results about encoding brain dynamics in order to improve the phenotyping predictions of the HCP dataset. So the idea was to pre-train the model, the VSMAE model, on sets of multiple frames, and then use this encoder for sex classification. So if you look at the table, I'm showing you 3 different results. So I know it's a bit difficult to read, but essentially, if you look at the 3rd column, it tells you if the model was pre-trained or not, and on how many frames it was fine-tuned. So the first row was not pre-trained, but fine-tuned on 3, or trained, in this case, on 3 frames for sex classification. The second was pre-trained on 1 frame, and fine-tuned on 1 frame, and the last column, the last row was pre-trained on 3 frames and fine-tuned on 3 frames. So we have significant differences in behavior in terms of performance. So if you're not pre-training your model and you try just to predict sex from fMRI frames, you actually can't really do much. You achieve 58% accuracy. When you introduce pre-training, you actually start having some good results. And when you increase the number of frames that you have in your model for pre-training and fine-tuning, you actually achieve really good performance. So that suggests that modeling spatial temporal dynamics actually improve the cortical phenotyping prediction. The second approach is to transfer learning. So here, the way it works, we set up the experiment was to assess the potential of VSMA to transfer learning by training a model on a very large data set. So here, the UK Biobank on 4,000 subjects, and then fine-tune it on different splits of the DHCP data sets, 10% of the data, 20%, 50%, and the entire model. What we can see is that when we pre-train the model, then during fine-tuning, we have a huge boost in performance on smaller splits of the training data. So in conclusion, the VSMA pre-training is an effective way to learn strong representation from static and dynamic cortical maps. It leads to better performance on phenotyping prediction tasks and can transfer to smaller data sets. The strong performance in terms of reconstruction suggests that the model can learn actual dynamic cortical function and spatial temporal patterns. And this opens the door for future application in terms of fMRI encoding and decoding of human brain activity. Thank you very much for listening and for your time. Yeah, I'll be here for the oral session if you have more questions. And thank you again to all my co-authors.
Thank you very much for the talk. If you have questions, please raise your hands, and hopefully we have some people with mics coming to you. Okay, so I'll start just with one. You mentioned that if you, depending on the amount of data that you mask, of patches that you mask, you get results in a reconstruction that tend more towards population specific or more towards subject specific. One thing I was wondering, and maybe that depends also on if you do positional encoding and how, is there an impact of the distribution, the spatial distribution of this mask? So some regions are more anatomically variable, for example, between subjects. Did you look at this idea of spatially stratified sampling, or do you just sample randomly?
That's a great question. Actually, I tried initially to sample specific region because that data set was super interesting. It was movie watching experiments, so you would expect, for instance, visual cortex or auditory cortices to be more activated. So actually, this is going to be like the subject on another work that I'm working on at the moment. But in this case, I did it randomly. I didn't focus on specific regions, but definitely that would be interesting. For instance, masking the entire visual cortex, just looking at all the cortices and see if you can actually reconstruct any information from that. Yeah, but yeah, I didn't did it for this paper yet.
Any other question? Okay, let's thank the speaker again. Thank you.
Okay. So the next talk will be by Pranav Kulkarni on hidden in plain sight, undetectable adversarial bias attacks on vulnerable patient populations.
Good morning, everyone. My name is Pranav Kulkarni, and I am from the University of Maryland School of Medicine, and today I'll be presenting this paper that our focus is on undetectable adversarial bias attacks. So adversarial attacks in the context of medical imaging are essentially where an adversary targets a deep learning model with the intention of impacting patient health outcomes. And specifically, we focus on bias attacks where the goal is to inject bias within these models. And these can be undetectable because we focus on vulnerable patient populations, which are not only underserved in clinical settings, but also underrepresented in the data sets that we use. So the overarching question that motivated us was, can we target a demographic group by injecting undetectable underdiagnosis labeled bias? So We primarily focus on label poisoning attacks, where an adversary manipulates the labels of certain images within the training dataset for a deep learning model, such as in this example where an adversary targets pediatric patients and flips positive labels to negative labels. And this type of bias is known as underdiagnosis bias, which landmark papers such as this one published in Nature Medicine have shown to have disastrous clinical consequences. So let's say a deep learning model takes this manipulated data set and is trained on it, and let's say it's deployed. In this type of attack, if a pediatric patient is encountered by the model makes a biased prediction. So these types of attacks on deep learning models and their implication in the clinical environment is an underexplored field of research. So our hypothesis going into this was, can demographically targeted adversarial attacks introduce undetectable underdiagnosis bias in a chest X-ray deep learning model for pneumonia detection? So for our bias attacks, the goal is that we want to target a demographic group by injecting underdiagnosis label bias across varying rates. In this case, let's say an adversary was targeting pediatric patients, and our control group is an adult chest X-ray. And in both cases, the patients have pneumonia and are initially correctly classified as positive for pneumonia. But as more bias is injected, as you can see, the probability that the pediatric patient is misclassified as not having pneumonia increases. And in this case, the rate that we mentioned earlier is essentially the proportion of positive finding images that we flipped to negative finding. So how do we measure whether an attack was successful? So there's two key terms that we measure. The first is bias selectivity. So let's go back to the figure from earlier. What we mean by bias selectivity is that the model only impacted the targeted group and the other demographic groups were not affected. This sort of alludes to the undetectability of these attacks, as in the context of underrepresented groups within these data sets, this will make up a small set of incorrect predictions and a large set of mostly correct predictions, and are, as a result, hard to detect. The second is bias transferability, where let's say we observe a bias on an internal data set against the pediatric group, but when we extend and apply our model to an external data set, we continue to see this bias translate to external data sets or even in clinical deployment. So the big question is, how do we quantify these two factors? So to do this, we propose a new vulnerability metric, and I'm not going to bore you all with the math. I know it's really early in the morning, so let's mention the key points. So vulnerability essentially indicates whether the adversarial bias attacks impacted the targeted group's model performance with respect to the overall model. So when V is negative, that means the disparity decreases with increasing rates of bias injected. When V is 0, there's no impact. And what we really focus on is positive V values, where disparity increases with increasing rates of bias injected. And that's how we can conclude that the model is biased, and in fact is getting more biased as we inject more bias into the training data set. Another point is that a larger V also indicates that a group is more vulnerable to undetectable adversarial bias attacks. Such as in this case where we have group A and group B. The disparity for group B is much higher than that of group A, so we can conclude that group B is more vulnerable than group A. Another point is that vulnerability also indicates whether bias transfers to external data sets. So let's say we observed a positive V value on an internal data set, and then we also observed a positive V value on the external data set. We can conclude that the bias transferred to the external data set. Now, in the case if we observed a negative V, where the disparity decreases with relation to the overall model, we can conclude that the bias does not transfer. So this is the math, but you can read the paper for the full details. So our focus is on the RSNA pneumonia detection dataset that we use for training, validating, and testing, and then we have the MIMIC and CheckSpurt datasets for external testing. We use 17 demographic groups, 2 sex groups, 5 age groups, and 10 intersectional subgroups, and these groupings are what was established in prior literature. So our experimental design is as follows. For each targeted group, we manipulate the RSNA training and validation sets across 7 rates of underdiagnosis bias. We train DenseNet 121 models with 5-fold cross-validation. We test these models on clean, unmanipulated RSNA, CheckSpurt, and MIMIC test sets. And then we measure the false negative rate for each demographic group and the overall model. And we measure the vulnerability V for each demographic group. So for the sex groups, what we observe is that the female group is more vulnerable than the male group. As you can see, the disparity between the overall model and the female group in the right figure with increasing rates of bias is more than that when the male group is targeted in the left figure. If you look at the vulnerability values, what we observe is that the bias is highly selective on the targeted group, which was females in this case. And we also observe that the bias translates to external data sets. We also see the same trend when the male group is targeted. While this effect is smaller than that in what we observe at the female group, we do see that this bias is highly selective and translates to external data sets. Looking at the age groups, we observe that the 0 to 20-year-old group is the most vulnerable, and the 40 to 60-year-old group is the least vulnerable. As you can see in the left figure, when the 40 to 60-year-old group is targeted, there's hardly any impact on the performance with relation to the overall model. But if you look at the right figure, when the 0 to 20-year-old group is impacted, there's a massive jump in the false negative rate with relation to the overall model, and in fact, even the other demographic groups. So if we look at the vulnerability values, we continue to see a high selectivity for bias, which is indicated by positive v-values on the diagonals. And more interestingly, we see that this trend actually translates to external data sets as well. Now, there's a lot of comparisons here, so for the sake of time and everyone's sanity, I'm going to only highlight some of the key findings that we observed in this. The first is targeting the 60 to 80-year-old group also affects the 80-plus-year-old group. And this finding is important because the 60 to 80-year-old group is a minority group in the RSNA dataset, but in the Shakespeare and Mimic dataset, it is a majority group. That means these types of attacks can be independent of demographic distributions between datasets. Another interesting point is that in the RSNA dataset, we actually observe that there is bias on the 0 to 20-year-old group, but when we look at the external datasets, the bias is missing. And the reason for this is that pediatric patients are absent in the Shakespeare and Mimic datasets. So what we actually observe is that the 0 to 20-year-old group behaves more like the 20 to 40-year-old group with the external datasets because it has patients aged 18 to 20. Now, there's even more comparisons here with the intersectional subgroup analysis, but the general trends are that we continue to see high selectivity for bias. We observe that the male 0 to 20-year-old group is the most vulnerable, and the female 0 to 20-year-old group is the least vulnerable, which is interesting because earlier we just saw that the 0 to 20-year-old group was the most vulnerable. What's even more interesting is that targeting the male 0 to 20-year-old group also impacts the female 0 to 20-year-old group, but the other way around is not true for some reason. Because when targeting female 0 to 20-year-old group, it only impacts the male 0 to 20-year-old group. When we look at the external data sets, we see that the vulnerability and bias selectivity also transfers to the external data sets. We do see a very similar trend with how the 0 to 20-year-old group behaves like the 20 to 40-year-old group in the external data sets because the pediatric patients are missing. There's also an interesting interaction between the female 40 to 60-year-old group and the female 60 to 80-year-old group where targeting one group impacts the other group and vice versa, and this also translates to external data sets. So what are some key findings from this work? The first is that adversarial bias attacks can introduce undetectable underdiagnosis bias in deep learning models. They demonstrate high selectivity for bias in the targeted group, and they result in biased deep learning models that can transfer bias to external data sets. And these types of attacks are feasible because a lot of it stems from the importance of local optimization over generalization in deep learning. For example, groups with similar characteristics, these could be anatomical, pathological, can be associated with incorrect predictions and lead to biased predictions between groups without similar characteristics, such as male versus female. Another point is that deep learning models can learn demographics as triggers for biased predictions. Essentially, as we all know, deep learning models can encode certain protected features, such as demographics, and these can lead, when features like this are encountered during inference, it can trigger the deep learning model to make a biased prediction. And in fact, a lot of these types of attacks can be hard to detect because labeling errors are so common within the data sets that we use. In fact, a lot of the feasibility of such type of attack can happen at any stage of model development, such as during data curation, where we can have biased automated labelers. There can be clinical biases, not just human biases, but there's been also some papers that show that financial conflicts of interest can also have an impact. And after data curation, during training of models, there can be man-in-the-middle attacks or backdoor attacks. And in fact, a lot of these methods don't even require access to the dataset demographics because literature has shown that deep learning models can predict demographics with high accuracy as well. So there's some ways of mitigating these types of attacks, and a lot of it is demographic reporting in datasets because it enables us to do subgroup analysis for bias and identify whether there are hidden biases within deep learning models that we use. And there's obviously the importance of curating of diverse datasets for better generalizability. But these are all passive solutions that a lot of times we don't really have a control over. So what can we do as a community? We can employ more active defenses against these types of attacks. Label poisoning attacks are have been explored pretty much in depth in computer vision literature, but the key difference is that a lot of times they focus on label noise rather than label bias, which is what we showed in this work. And they have shown that some defenses have high success rates, but the challenge is that we're focusing on label bias, so it's not clear if these defenses also do translate. Another interesting challenge is that in this work, we only focus that an adversary targets only on one group, but in fact, in the real world, multiple groups may be attacked at the same time. So future exploration is needed in what type of defenses that we can use to prevent adversarial attacks against the models that we develop. So in conclusion, what we show is that our work is a crucial first step in highlighting the implication of undetectable adversarial bias attacks on deep learning models in the clinical environment, and such attacks can scale across various applications of deep learning in medical imaging and target vulnerable patient populations. So I want to thank everyone in the audience, as well as my mentors and the team for their support throughout this project. Thank you.
So thank you very much for the interesting presentation. So I think we have a question over there.
Does the microphone course continue? No. Okay, awesome. Thank you for the presentation. Very interesting exploration. I was curious about your thoughts on kind of further expanding this research, because what you presented is on an example of one network of 3 data sets and of very selected subgroups that you know in advance. Mm-hmm. How do you think this could kind of expand in future to be less dependent on the network, the specific predefined groups on the specific data sets?
So I'm going to try to answer that question in multiple parts. So you mentioned specifically network architectures. So in the full paper that we have the QR code for here, we do analysis on multiple network architectures as well, and we do see similar trends. So that part, I think we have established that these types of attacks are not network dependent, but can scale across various different architectures that we use. In regards of future work, I think these types of attacks essentially rely on the fact that deep learning models can learn these demographic features, and a lot of it is associating these demographic features with biased predictions. And if that is possible, then these types of attacks are feasible in pretty much any application, as long as you have some association with certain protected features that can be used to exhibit bias in a deep learning model. I hope that answers the question. Okay, yeah.
We have a bit more time for another question. All right, thanks. Yeah, thanks also for the talk, very interesting exploration. If I understood correctly, you mentioned that when you have an adversarial attack on female, you don't have a pretty big transfer to the male group, and vice versa, right? So I was wondering if you looked at the images, and also if you had kind of feedback from the clinicians explaining why a check stray from a female an attack on female group won't have a big impact on the male group, thinking about the check stray images.
That's a pretty good question. I think we have not really consulted clinicians on what are the differences in the images that could lead to this. a lot of the trends that we observe with how we observe bias in this, in the results are pretty much what other papers have also shown. There's a lot of papers that show that female groups are more vulnerable to exhibiting bias in deep learning models, and there needs to be work done as to what parts of these images, and not just for simple sex groups, but also for other factors from age, intersectional. There's work that includes insurance and race and ethnicity. So there's so many different factors that we have to account for that it really is an exploration into what really is associated. And I think that is something that could be an interesting future work to look at, is that what parts of these images, is it shortcut learning or is it something else?
Thank you.
Yeah.
Yeah, you can go ahead, but a quick one, please.
Okay. I mean, great work. I just had a question around what's the next step? Should we look into the shortcut features that the model is predicting for each demographics and try to make it agnostic to those features, or do you want to expand and have more augmentation in terms of demographics so that the model cannot pick up specific features to each demographic? What's the future step for these?
Yeah, that's a really good question. So I think the next step is identifying potential defenses. So like I mentioned in this case, these types of attacks are this can happen in multiple different stages, even without looking at images as well. They can be automated, labelers that are also biased. So there's a lot of factors that we need to look at, and it's not just about developing strategies so that when we have a data set of verifying if there is no manipulation done, to identifying what features that the model is learning that can be associated with these predictions. And I think there is pretty much because a lot of this type of work hasn't really been explored really, especially in the context of bias. Adversarial attacks have been explored, but in the context of bias, it's still not clear as whether even the defense strategies that a lot of people have implemented for standard label poisoning attacks will work in these cases. And that a lot of it is future work, and I think the direction is to not just look at the data that we work with, but also actively include defenses, because when you're curating a data set, it's hard to verify. If you're working with hundreds of thousands of images, it's hard to verify every single image. So defenses that identify, this could be standard bias mitigation strategies that have been explored in medical imaging literature. And these could be standard label poisoning defenses. So I think a lot of the future direction is linked with how do we incorporate these active defenses against this type of attack.
Okay, let's thank Pranav again, and let's move on to the next talk.
Our next talk is an unexpected confounder, how brain shape can be used to classify MRI scans, presented by Valentine Varnier-Dauchel.
Hi everyone, so today I will talk about an unexpected confounder and how brain shape can be used to classify MRI scan. This is a paper 359. So first, what is a confounder? If I want to train a classifier to distinguish shapes, for example, ellipses and rectangles, I can use this type of dataset. Unfortunately, in this case, the classifier can also use the color to distinguish the two datasets instead of the shape. So the color will be a confounder. This type of bias can lead to a lack of reproducibility and confidence, while classifiers are largely used for diagnostic or in other models like GAN or guided diffusion models. Several confounders have been identified for brain scan classifications, and in this work we have said that the brain shape is also a confounder for this type of task. So that is to say, when I train a classifier to distinguish two brain scan datasets, for example, a healthy one and a pathologic one to detect a pathology, the brain shape can be used by the classifier to take its decisions. Thank you. Yeah. So in this work, we have the following contribution. First, we identified the brain shape as a confounder, while it has never been considered as that. Then we propose a rigorous and generic method to assess if a covariate is a confounder or not. And finally, we propose a brain shape normalization using deformable registration to cancel the brain shape confounding effect. So our verification method is in two steps to answer the following question. Is a covariate a confounder for the classification of two datasets? So for the first step, we wonder whether it is possible or not to distinguish two databases using the suspect covariate. If we come back to the example of color and shape from the beginning, it means that we will train and evaluate a model using only colors as input and check if the classification is possible. For the second step, during inference, we will modify the input such as the covariate is in the distribution of the opposite class and check if its impact the classification. For the color shape example, for example, we can switch the color of the cycle from red to blue and evaluate the impact on the classifications. For the brain shape confounder, we apply this method by representing the brain shape with the brain mass. So for the first step, we will train the classifier using the brain mass as input and the same classes and labels. If for the test it is possible to classify the brain mass, then the brain shape could be a confounder for this classification task. Conversely, if it's not possible to distinguish the two databases with only the brain mass, the brain shape can't be a confounder. For the second step, we will train the classifier with the original data, classes, and label. And at reference, we will compare the classification performances between the original image and images with transformed shapes, such as the shape is in the distribution of the opposite class, while modifying the image as little as possible. For this, we propose two transformations to change the shape from one class to another. We draw a random mass from the opposite class and use it to either crop the brain or realign the border thanks to a brain border deformable registration. If with this transform image the accuracy decreases compared to the original image, then the brain shape is used to classify the data set, and so it's a confounder. So for the second transformation, the brain border registration, we solve this optimization problem. So it consists in finding a deformable registration between the brain borders of a reference image and a moving image. We also add some regularization to avoid too strong deformations. Finally, for our last contribution, we propose to remove the brain shape confounding effect to add a step to the preprocessing pipeline classically used for brain scan, and which we'll call shape normalization. For the shape normalization, we use the previous brain border deformable registration with as moving images all the images of the data set to be processed, and as reference image, a single image, a template, and in your case, the MNI atlas. For our experiments, we train a binary classifier with several data sets. Some are healthy, some are with a pathology, for example, multiple sclerosis, tumor, and Alzheimer's disease. And the age also varies by datasets. So for here is a true negative rate, true positive rate, and balanced accuracy for the brain mass classifications. So for this first step result, we can see that we are able to distinguish brain mass for almost all the datasets with an accuracy, a balanced accuracy higher than 90% for 4 combinations of datasets. And the only exception is the intra-dataset classifications. So indeed, we are able to classify both LC versus pathological dataset and LC versus LC dataset, even when they match in age. Conversely, for the intra-dataset classification, the Alzheimer's disease is not enough to distinguish the brain mass from the 2 classes. So it seems that the brain shape difference is more linked to a dataset construction effect that is not removed when disease or age factor are removed, but which is removed for an intra-dataset classifications. For the second step result, on the right, you can see an example of image and transform shape images with both crop images, with both crop, for which the part outside of the drone mask are removed, and the register one for which the brain border fits with the drone mask. Quantitatively, we plot the true positive rate and true negative rate for here an LC versus a tumor datasets. So we can see that the classification performances for the original image are perfect in blue, whereas for the transform image, either crop or register, the accuracies decrease by 40 and 60%. We also apply elastic deformation as data augmentation during training to introduce shape modification during the training, and we can see that the classification performances decrease less with this data augmentation, but the classification is still affected when the transform image is used at inference. With the normalization, the classification performances when we use the transform image are almost no longer affected, and the data augmentation seems less useful with our normalizations. If we visually, with our normalization, the shapes between the shape of the 2 classes seems more similar. If we look at the attribution maps, which highlight the areas that are useful for the classifier decision, we can see that without our normalizations, the attribution are focused on the brain border, whereas with our normalization, they are spread in the whole brain. If we look at the result for the other databases, we have similar results, and we can see that the brain shape influence the classification, and so is a confounder for most of the data sets, as the accuracies decrease for transform images. And our shape normalization remove the confounder influence as there is no more decrease with the transform image. For the last cases where the brain shape is not a confounder, our normalization, our shape normalization doesn't impact the classification, and so it's not a problem even when the brain shape is not a confounder. So to conclude, we show with our method that brain shape can be a confounder for brain scan classification, and we advise to systematically use our shape normalization as a step of the preprocessing pipeline, as it eliminates the confounding effect of branching without degrading the classification performances. Thank you for your attention, and please note that my poster is upstairs and not with the other oral sessions. Thank you.
Thank you very much. What would you like to ask about this presentation? Please raise your hand if you'd like the microphone here in front and then in the right.
Hello, thanks for the presentation. Just a question, when you make the first step before the shape normalization, are the brains affinely registered on the template?
Yeah. We use classical preprocessing pipeline, so there is an affine registration on the template. But for the images with shape normalization, we add in addition to the affine registration or shape normalization based on deformable registration.
Another one on this side as well.
Hi, thanks for the talk. I'm a bit confused, and I would like your view on one point. So morphometric analysis has been something quite extensively used, where we actually study the shape of brains to extract phenotypic information about disease so that we can differentiate diseases. Are you saying that all of that should go into a bin and we should not focus on the shapes of brain? I'm a bit confused by the message you're conveying.
Yeah, I think it depends on the application, and the user must choose if the shape is a relevant information or not. But as it is possible to distinguish data sets that are healthy with age that match, there is unfortunately a construction effect linked to the brain shape difference.
I'd like to know, thanks for the talk, first of all. On slide 6, for instance, you have these bars, and I noticed that most of the bars go up to 1.0 for the true negative rate and the true positive rate, I think. Is it a relative measure or an absolute measure? Did you normalize and if so, what were the absolute classification?
For the first type classification on brain mask? Yeah? I don't hear you very well.
Sorry.
It's better.
The mic is a little bit off. On slide 6, for instance, the bars, are they normalized or so absolute or relative measures? Oh, slide 6 has no bars. Maybe, sorry, maybe the next one. Or where are the first bars with results? I thought I looked at maybe I misremember.
Yeah.
You know, when you have the bars that go up and down for true positive and true negative, for instance.
Well, is this one?
Yeah, the first bar goes to 1.0. Is this meaning that the classifier is perfect, or is it a relative measure?
No, it's perfect. It's two positive rates, so it's the positive case well classified under the number of positive case, so it's not normalized.
Okay. Thank you very much.
Thank you.
Okay, so for the next talk, we'll keep going in the theme of confounders, and it will be Nima Prati that will present his work on decodex.
Okay, hey everyone, my name is Nima. I'm a master's student from McGill University and Mila Quebec AI Institute. Today I'm delighted to be here presenting my latest work, the Codex. But before getting us started, just wanted to thank all my colleagues, especially Amar Kumar, who has contributed equally to this paper, and my other colleagues from Mila and Google Research Montreal. So let's start our presentation with an example. Let's say that we have a patient that comes to the clinic and we have access to a deep learning classifier. And when we pass this chest X-ray of the patient to our deep learning classifier, we get that the prediction is sick. But when our clinicians wants to visit the prediction, they only see a binary value, so they cannot rely on the fact, and we need to gain a trust. In order to gain a trust of our clinicians, we need to open up this black box classifier by basically providing reasoning for the decision of the model. So let's say now we have explainability, and we show that in blue arrow you can see the disease pathology. So that's where our model is basically now focused. So we have gained the trust of the clinicians. So we have a lot of different explainability methods in the literature, such as Gibbs explanation, AttriNet, and for the sake of this presentation, I'm gonna focus on counterfactual explanation, which is also a backbone of our proposed framework. So going forward, we're gonna elevate the example to a scenario when, let's say we have a data set where majority of the 6 subjects, they have some sort of medical devices, such as pacemaker wires on their chest X-ray, and on the other hand, for the majority of the healthy subjects, we don't have such devices. So when we use an explainable model in this case, we're gonna see that the focus of our model is on the visual artifact or the pacemaker in this sense, and we're basically able to expose the bias, but because of these strong correlation, we are able to do the correct prediction, but we are actually right for the wrong reasons, because we are latching to this confounder, and we are not making our decision based on the disease pathology. So let's say that in a case that we have another 6 subjects that comes to the clinic, but this 6 subjects doesn't have any such sort of support devices, then we are basically going to fail to generalize in that sense. And also another problem is that we are not mitigating the bias yet, and we are just exposing it with a counterfactual or with an explainability model. So just in brackets, I'm gonna say that there are some sort of methods such as group DRO for mitigating the bias, but the caveat is that you need to have subgroup information, and you need to basically have you need to know whether the patient is sick or not, and whether the artifact is present for each of your examples. Going forward, in order to address these problems, we're gonna propose the Codex, which is basically a counterfactual explanation method that focuses on the pathology rather than the confounder. So in our method, let's go back to the same example. We have the visual artifact on the right top, and disease pathology on the bottom right side of the image. And now, instead of just classification, we are going to the answer to the following question: that what would this person looks like if they were not sick? So when we pass this image to our model, we're gonna end up with something like this. If you look at the disease pathology, you can see the changes are happening in that area, and there's little to no changes in the shortcut. So we are basically ignoring the shortcut in this case. So before getting into the details of the architecture, just a quick note about the dataset that we're using. In this work, we are using Checkspread, which is a public dataset, and we are basically using the same scenario here when we call it device dataset, where the confounders are the visual artifacts or wires and pacemakers. So as you can see in this figure, the majority stands for majority of sick patients. You can see we have the visual artifact in this case, and for the majority of healthy subjects, we don't have such artifacts. We also propose another contrived data set, which is basically a synthesized dot confounder in order to show the workings and the versatility of our model. So in this case, we have the dot data sets fixed in the one location for the majority of the 6 subjects, and on the other hand, there's no synthesized dot on the healthy patients. So for the architecture, we are basically proposing a guidance in the inference time with the use of diffusion models. So let's say that we have an input image, plural fusion. We first crop this image with noise, then we go through some sets guidance steps in order to get our counterfactual image. But the question is that how do we get there? So we have to just now open up these guidance steps and go through them step by step. So each guidance step is actually now consisted of 4 different stages. The first stage is basically when you have the noisy image Z of t on the top, you use an unconditional DDPM that you have trained earlier. It can be any pre-trained off-the-shelf unconditional that you use. And after cleaning the image, we're going to end up with the X of t. We pass this image to 2 different classifiers. The first one is a black box disease classifier, which is just a binary classification of the disease. And then there's a confounder detector, which is also the binary classification of the presence of the confounder. And note that in here we are using pre-trained and frozen classifiers, and you can also use any off-the-shelf classifier for these 2 modules. Then we're gonna calculate our loss, which is also consists of 3 parts. The first one is called classifier consistency, which basically we make sure, let's say that if the input image is sick, we're gonna end up with a healthy counterfactual. The second part is artifact robustness, when we make sure that if the input image has the artifact, we're not gonna remove it, and if we don't have any artifact on the input image, we're not gonna add any external confounder. The third part is also identity preservation, which is a classic loss in a counterfactual explanation. When you want to make sure that the generated image has the same identity and you're not changing the identity of the subject. After calculating the loss, we're gonna shift the distribution of the Z of t to Z of t minus 1 with this trick, and we're gonna resample from this new distribution. And we claim that if you repeat this procedure for like 50 iterations, you're gonna end up with a counterfactual which is in the correct distribution of the space. So for the experiments, we have 3 different experiments. The first one is just the qualitative results when we are gonna show how we mitigate the bias. So in this picture, you can see that on the left, we have original image. You can see the disease pathology with the blue box and with the artifact or the confounder with the red box. So on the right side, we have decoded, which is our proposed method. And in the middle, the baseline, which has the same architecture as the codex, but this time without the confounder detector or the green box in the previous slides. So if you compare the results, you can see that in the baseline, we are just doing shortcut learning. We are removing those red boxes, and we are not doing anything in regards of the disease pathology. But on the other hand, with the codex, the changes are happening more around the disease pathology, and there are little to no changes for the visual artifact. So we can say that we have ignored the visual artifacts in our model. In this case, we are going to go through some metrics. So we can also divide the metrics in 3 different subgroups. The first one is the L1, which basically measures the similarity of the counterfactual and factual images. Then we have counterfactual flip ratio and counterfactual prediction gate when we measure the alignment of our counterfactual with the target label. And the third, which is the most important section for us, is the detector robustness ratio and spurious correlation latching score, when we measure if we were able to ignore the spurious correlation and the confounder and focus on the pathology. So if you see all the results, we are consistently almost better than the codex in all cases. But when it comes to the second and last row, we see a huge boost in the performance, which shows that we are in fact able to ignore the artifact and focus on the disease pathology. There's also another downstream task when we basically measure the accuracy of the counterfactually augmented classifiers. But in order to understand that, we first have to define the dataset augmentation pipeline. So I'm just going to take you through this picture. So we have the original dataset or our CheckSpert dataset. We generate some counterfactual images with the baseline model or the codex, and then we add those generated data to our training data, and we have now a bigger data set. We pass this to our classifier, which can be an ERM classifier or a debiasing method such as group DRO, and we end up measuring the subgroup accuracies for each of our majority and minority groups. So by doing that, we can first see the results for ERM. The green columns are denoting the majority groups, and the red columns are for the minority groups. So when you see all the majority groups, you can see that all the models are consistently good in that case. But when it comes to the minority subgroups, you can see that ERM and ERM that is augmented with the baseline counterfactuals is basically not able to do any predictions. But on the other hand, when we add the decodex counterfactual, we see a huge boost in performance. For both data sets, we can see this is the this is basically the trend. And we can say that the codex counterfactuals can help with the performance of the minority subgroups. But there's also another section of this experiment when we have access to the subgroup information, so we can train the group DRO, the debiasing method. So let's just see the case in here. We are basically seeing the same behavior. The majority groups are working perfectly for all the cases, but when it goes to subgroup minorities, we can see we gain some also performance when we use the baseline with the codex. On the other hand, the augmentation with the codex, but when we do augmentation with baseline, we see drop in performance. For example, you can see the second row of the first table, we see a drop in performance with the baseline counterfactuals. So the take-home message is that we had the opportunity to say that the codex is all you need in this case. And going forward, as a conclusion, we can see that the codex improves reliability and trustworthiness in AI. And we basically improve the explainability. We do generalizability for classification and minority groups. Unlike the debiasing methods such as group DRO, we don't need the subgroup information. We only need to know the presence of artifact for each subject. And this is also flexible to use any off-the-shelf detector. At the end, I just wanted to thank our sponsors, also you audience, for listening to and having attention to my presentation. Feel free to scan this QR code, and also I invite you to join our poster presentation, which is and have more in-depth discussions. Thank you.
Any question? There's one here.
Thank you very much for the talk. I wanted to know if you had any idea, because since you train, in a sense, a network to try to detect the presence of a confounder or not, do you have any idea if it would scale, this method would scale well to multiple different possible confounders?
I'm not sure if I got your question correctly. So do you mean like with different data sets or?
No, if you have a data set where you could have multiple different confounders.
I see. I think there's nothing to stop us from having different sort of like the confounder detectors. We haven't tested that, but I would believe if there is a sparse correlation with like different things, you can even use anything other than the binary multi-class prediction with the confounder, or have like different confounder detectors together.
Oh, there's a question over there.
Well, very interesting talk, and I noticed that you here.
Oh yes, sorry.
And I noticed you focus on two types of confounders, including DOS and devices. And actually, I read papers about that the words on the X-ray image also a general confounder. And have you conduct experiments about the word confounder? That is, for example, in page 6, the word at the top left, the third image, maybe the word up at the upper of the image.
Mm-hmm. Actually, like on Shakespeare, I think we don't have access to those information. Like if you're talking about like these words on the top right as the watermark, there is no, I'm not sure, but I think there's no like label for those things. So honestly, we weren't able to train a confounder on that, but that would be a very cool idea if there's like annotation for that.
Yeah, actually, I trained classifiers on these images and found that the activation map has some highlight on the word.
Yeah, exactly. We have also seen, and in fact, when you use diffusion models, because of the way that diffusion models do stochasticity, we see that sometimes these things also change with the diffusion. So that's a problem that I think someone need to probably add some annotations or some labeling in order to make sure that we are not messing these watermarks. Yeah.
Okay, thank you.
Hey, thanks a lot for the talk. That was very interesting. Yeah. I just have a slightly more practical question. So the annotations for on the real data set, are those publicly available, or is this also something that you generated?
So the cool thing about our paper is that we are not using any masking. So when I say that these are the visual artifacts, we are only using a binary label. So there's a 0 or 1. So it's not with a mask on the diffusion. So we have like very limited like supervision on the diffusion. But these like labelings are available on the Checkspert. But for the bounding boxes, I think there are some other data sets, but we are not using any bounding box or such information.
Okay, thanks for clarifying. I thought you had annotations on a pixel level. So it's
No, it's just a binary classification with the this green box in here.
Okay, yeah. Thanks.
No worries.
Okay, thank you very much for the nice talk and questions. And let's thank the speaker again.
Okay, our next talk is parameter efficient generation of natural language explanations such as chest X-ray classification presented by Isabel Riototo.
Okay, hello, good morning. My name is Isabel, and it's a pleasure to be here talking about parameter efficient generation of natural language explanations for chest X-ray classification. So for the sake of time, I will not introduce the need for explainability. Other colleagues have done so. And I just want to maybe mention that the most common type of explanations that we usually see are visual explanations, so like saliency maps, heat maps, attention maps, so something like this. Where this points to what or where the model is looking at. But in this work, we focus on natural language explanations, or NLEs, and they are essentially textual descriptions of the decision-making process of a model for a given image. So it's kind of a combination between an image caption, an image description, and also the model prediction. And they are intrinsically understandable by humans in the sense that it's text. And they can, of course, be complementary to visual explanations. And in the medical domain, they can be specifically useful because they also correspond to how radiologists explain their diagnosis, for example, with medical reports. And in this work, we focus on the generating NLEs for multi-label chest X-ray classification, and we start by using the paradigm and also the data set introduced in a paper on MICAI 2022. And essentially, very briefly, what they do is they have a decoder NLE generator that not only takes into account the features from a vision feature extractor, in this case DenseNet 121, but also the prediction of the model. And since this is multi-label, they actually generate one explanation for each label for each image. We also use the dataset proposed in this paper, which is Mimic NLE, which is based on Mimic CXR. And yeah, we have one ground truth NLE for each predicted label. So, as we know, we're always talking about these kinds of things, that annotation is expensive, and for NLEs in the medical domain, of course, we need experts. So we asked ourselves, can we generate these NLEs without requiring full supervision, and how could we do this? And I just want to stop here and make it clear that in this work, we actually are still working with full supervision, but this is a first step towards lowering the supervision, okay? So what is the problem with if we in the future want to do less supervision in NLE generation? So for those of you who might not be familiar with autoregressive text generation, I just want to briefly explain it. So if we have, let's say, a starting word, essentially it goes through the model and it predicts the next word, and then this next word is appended to the first word that we had, and so this sequence is fed again through the model to predict the next word, and so on. So this is like how ChatGPT answers our questions, basically. But the thing is, so this is what is used during inference, and this is what we call the paradigm without teacher forcing. And you might notice here that when we have the ground truth text, we already know what's the next word that we want to predict. So in fact, we don't need to wait for the generation of the previous words in order to predict a certain word. So what is actually done usually in practice during training is this teacher forcing paradigm, where we just feed all of the words at a time, and in parallel this generates the next word. So this is much faster, of course. And this is the normal training paradigm for these systems. But the problem is, if we want to progress towards less supervision, we won't have these ground truth text to do this teacher forcing paradigm. So basically one possible solution would be, I don't know if this will work, but let's, for the sake of the argument, let's think it might, would be if we want to just supervise the explanation not word by word against a ground truth explanation, but we want a downstream model that just evaluates some properties of the explanations, so for example, clinical relevance somehow. And the problem here is text is discrete, it's not continuous, so gradient, the gradient wouldn't be backpropagated to the rest of the model if we wanted to do this. One possible solution would be to use reinforcement learning. I'm not an expert at all on reinforcement learning, but it's been known to be a bit unstable. Also, this would be slow because we would need to wait for a given word. We would need to wait for the generation of all the previous words. So another thing that we could do, and this is what we propose, is to replace this decoder by an encoder-decoder approach. And with this, we can actually learn the explanation or the text in the continuous latent space of the encoder, but at the sentence level. So we would ensure gradient propagation without needing reinforcement learning. And also, as a plus, this would give us faster training because now we would only need to forward one time to obtain a whole sentence and not n times for each word in the sentence. Furthermore, it is also possible to still decode this latent space into text because we would still have the pre-trained decoder. And so we wanted to validate if this approach would work in the fully supervised scenario first before moving on to the scenario with less supervision. So in the first phase, we just trained this text-to-text denoising autoencoder, and we achieve a blue force score of 93.9 on this mimic NLE dataset. But the thing is, in the first step, this is just text-to-text. So next, we need to adapt it to also receive the vision input and also the prediction from the model. So what we thought was, how can we maintain the structure of this encoder-decoder as much as possible, just adapting what we needed, and without also like changing the properties of the decoder, the encoder-decoder network, because it already knows how to generate text. So this is why we here explore parameter-efficient techniques that also been talked about in the conference during this week. So we only fine-tune certain adaptation layers. And we explored, I think, 5 techniques, but for the sake of time, I will just show you one of them. If you want to discuss further, come find me during this last day of the conference. And one of them is a Llama adapter, the multimodal version. So essentially what it does is it adds these soft prompts to every layer of the encoder and to every time step, to every word. And this way we feed the vision features and the prediction of the model through a vision to adapter. It's basically a transformer network to make sure that the dimensions match. And so this vision to adapter and this soft prompt are the only parts that are trained in a model. Everything else is frozen. And also we asked ourselves, okay, since this is the first step towards this future goal of less supervision, can we actually remove the decoder as we wanted? So until now, the supervision was done in the latent space of the decoder, in the discrete text space, where we would just compare the ground truth NLE with the predicted text with cross entropy. But can we remove the decoder and actually supervise in the latent space of the encoder with the ground truth NLE, of course, after it being passed through the encoder as well? So we just wanted to test if this was viable in this fully supervised scenario before moving on to the with less supervision scenario. So in terms of results, I don't want to bore you too much with this, but we did test several parameter efficient techniques, and as you can see in the almost the last column, the number of parameters compared to the baseline DenseNet decreases significantly, specifically compared to for example, the base autoencoder where we fine-tune everything. And we can see in general terms that we are able to lower the number of parameters drastically and still maintain competitive performance. So if you focus on this overall column at the end, we can see that with the Llama adapter multimodal, we achieve among our methods the best performance. So just for clarification, this overall score was proposed in the other paper that we are working on top. And so it's basically the multiplication of the task performance, so the AUC, plus this times this CLEV score, which is this clinical evidence score of the explanation, times the average of the BERT and the Meteor scores, which are text-based metrics to evaluate the explanation. And finally, if you look at the last row, which is what I call the mean squared error loss, which is this previous approach where we try to remove the decoder to see if this would be viable, you can see that we still maintain performance. Of course, in like the text-based metrics, for example, the blue scores, the rouge and the cider and spice scores, they are lower because the explanations start to differ a little bit more from the ground truth. But the evidence score, so the clinical evidence that's present in the explanation, it's actually the best score of all. So the information is preserved. It might just be given in a different format. So to conclude, we built upon this work, which tackled the problem of generating natural language explanations for multi-label chest X-ray diagnosis. So one explanation per label, per predicted label per image. And we propose replacing this decoder-only generator by an encoder-decoder network. And doing this replacement, we explore these parameter-efficient techniques to reduce the number of parameters drastically while maintaining competitive performance. And we did confirm the viability that of the proposal of supervising the NLE generation directly in the encoder latent space at the sentence level. So this is indeed a first step towards this reinforcement learning free generation of natural language explanations when no or few ground truth NLEs are available during training. So thank you so much for listening to me. If you have any questions you want to discuss further, come find me at the poster or during the conference. Thank you very much.
Thank you very much. So we have a first question here.
Thank you very much for the presentation. I have a question with respect to the application aspects. So have you validated the plausibility or like lack of hallucination in the explanation that is generated? And if yes, what kind of like methods, or have you considered these explanations with the physicians? So how they would consider them?
Yeah, okay, so in this work, unfortunately, no, we didn't have access to the physicians. We, of course, relied on automatic metrics that, you know, have their place, but not optimal. So we tried this clinical evidence score that was also proposed in the previous paper. So basically what they do is they get the explanation, they feed it through this Shakespeare labeler, and so it basically outputs a list of the pathologies that are present, like pneumonia, effusions, things like this. And so basically we compare these properties with the ground truth explanation and with our generated explanation. But yeah, hopefully in the future I'll be able to get some clinician's opinion. Yes, thanks.
Thank you. Thank you.
Hi, thank you for the presentation. That's not working again.
It never works for you, I don't know.
It is? Okay, yes. Okay, awesome. I was trying to understand correctly. So you create the explanations based on the visual features and on the prediction of the model, right?
Yes.
So isn't it in the end an explanation for such a decision based on the visual features and not the explanation that your classifier takes?
Yeah, that's a good question. I mean, we didn't explore this, but the thing is, the model does produce different explanations for the same image for different pathologies. So that's a good indication that it might be working, not just using the image features. And actually here in the block diagram, also, we don't only feed the image features, we also feed the prediction vector and actually the prediction label in text format. Yeah, I don't know if I answered your question, but yeah.
Sort of. So the prediction vector is already binarized. So that's not like class probabilities.
Yes, it's binarized. Yes, but then since we need to generate one explanation per predicted pathology, we also feed. I mean, you can see really well from this diagram, but it means that in this case, since you have, let's say, 2 predicted pathologies, you will feed the left part of the block diagram twice to the generation model. And each time you will give it the text. There it says edema for the first label, and you would feed the other pathology name for the other label. Yeah.
I see. I'm just a bit concerned that you decouple the logic in the classification, like in the visual classifier, from what the explanation presents.
Yeah, I also share your concern. This is kind of a problem with also like post hoc methods, for example. Here, this is a bit diminished since the NLE loss is propagated also to the classification part. So the classification is also being influenced by the NLE loss. But yeah, there's a chance that it might not be 100% faithful. But there's also not good ways still to measure this. So working on it. Thanks.
Okay, thank you very much. Let's thank the speaker again.
Thank you.
Okay, so the next presentation will be by Raoul Salé-Dechoux on finite volume informed graph neural networks for myocardial perfusion simulation.
Good morning, everyone. So thanks for the introduction. Today I'm going to talk about finite volume informed graph neural network for myocardial perfusion simulation. So over the recent decades, patient-specific models have been developed for the study of coronary artery disease, or CAD. So for example, Hot Flow Company developed the FFRCT analysis, where blood flow and pressure in the coronary arteries are simulated to identify significant flow-limiting lesions. Another diagnostic tool for CAD is perfusion imaging. This imaging techniques enables the assessment of ischemia in the myocardium resulting from a disease in the coronary circulation. And so right now there is a growing interest in models that can simulate the myocardial perfusion using CT scans directly. So this is why in the previous study, a simulation pipeline has been developed for myocardial perfusion. So contrary to FFRCT analysis, this model incorporates a synthetically generated tree which is grown from the outlet of the large coronaries, segmented coronaries, to simulate blood flow distribution in the myocardium. So because of the addition of this synthetic tree, the computational cost of this problem is quite high, and we would like to reduce this cost by using deep learning method. And for that, first, we would like to replace the hemodynamic models that appear in this simulation model. So first, we need to replace the perfusion solver in the myocardium. So indeed, beyond the synthetic trees, in order to account for smaller arteries and capillaries, blood flow is modeled in the myocardium as a fluid going through a porous medium. So more precisely, we use a single compartment Darcy model with the pressure source term coming from the solving of Navier-Stokes 1D Navier-Stokes equation in the segmented and synthetic networks. So here we'd like to develop a machine learning model which can take as input a pressure source map and which would output the solution of the Darcy equations. So we need to find an architecture that can be trained on multiple meshes with different shapes. And also we would like this architecture to output the pressure on every node of the mesh by taking into account information from the surrounding nodes. So for that, we use a graph attention neural network. So this network can be applied on graph or meshes, and it starts with feature vectors for every node. So for example, for us, the node would be the mesh vertices, and the feature vector would be composed of the vertices coordinate and the pressure source values. And then the network can update those feature vectors thanks to graph convolutions and with attention coefficients also. And then if we stack multiple convolutions consecutively, we can exchange information from further and further nodes. So now about the loss. So classical deep learning method for a problem would use supervised loss. So classically, mean square error of the prediction of the network with a ground truth, which could be computed here using classical numerical method. But recently, a new class of physics-informed neural network has emerged called physics-informed neural network, or PIN. Instead of minimizing an error with regard to ground truth, those models try to minimize directly the residual of the PD on some point of the domain, so by injecting the PD directly in the loss function. So for that method to work, we need to compute the derivatives of the output of the neural network. So classical PIN method use the automatic differentiation framework for that, but the main problem here is that it can't generalize to new boundary conditions or new shapes. So another method to compute derivatives could be the finite difference method, which is a discretization method that can approximate the derivatives on the Euclidean mesh, Euclidean grid. So we'll see how, but those methods can allow to generalize to new geometries or boundary conditions. But the main problem here is that it can be applied on Euclidean grid only. So there are other discretization methods that can be applied on unstructured grid, like finite element or finite volume method. And here we will be using the finite volume method. So using this discretization method, in our case, we can obtain a linear system of equations that can be solved for Darcy pressure. In order to solve this system, we can use the Jacobi iterative method, which updates an approximation of the solution using the formula you can see here until we obtain a convergence. So we can notice that this formula is similar to what is doing the graph attention convolutions. So given this, the finite volume discretization and the later observation, we decided to implement a finite volume informed loss. So instead of using ground truth pressure, here we incorporated in the loss the matrix coefficients of A and B. And thanks to the Jacobi method, we know that if we minimize enough this loss function, we should obtain a good approximation of the solution. So here, if we take a step back, what we are trying to achieve is to learn a set of graph convolution that can be applied on a pressure source map and that can output the solution of the Darcy equations. And thanks to the nonlinear activation function and the network weight, we expect these models to generalize to new geometries and the pressure source map. So to train our model, we generated synthetic meshes. So by varying different parameters, we were able to generate 2,000 different meshes for the trained data set and 400 for the validation. And then we generated a synthetic pressure source map. So those synthetic pressure source maps are not super realistic, except perhaps for highly diseased patients, but this was done as a first approximation of a pressure source map. Then for the test data set, we used patient myocardial mesh extracted from CT scans, and then we generated a pressure source map using the same method as previously. Now here we compared our finite volume method with a supervised model that has been trained using the same architecture, but with the supervised loss against finite volume ground truth. So here all the errors are computed against finite volume ground truth. So first, if we look at the train and validation data set results, we can say that our model were successfully trained and can generalize to unseen geometries and pressure source map. So notably, we can see that the supervised model performed better on the mean absolute error, but it is the contrary for the mean max absolute error. And those observations are still true on the test data set, and even though the errors are higher, but this is what we could expect as our training data were quite different from the patient myocardial meshes. But still, while the supervised model obtained quite high errors on the test data set, we can observe that our finite volume model obtained more robust results on auto-distribution data. So here you can have a look at some results on two data from the validation data set. So overall, the results look good. We can observe some localized high errors. So those errors we can tend to be localized where the finite volume solution exhibits extreme values, but otherwise no location related to the meshes geometries were found about those high errors. So now here are the results on the two data from the test data set. So here now the high errors are higher and less localized, but we can make the same observation about the location of those errors. So to conclude, we developed a finite volume informed graph neural network to solve Darcy equations. Compared to classical network with supervised loss, our model does not require simulation data for training, and it showed promising results with regard to robustness on auto-distribution data, but still there are still some work to do to improve the mean absolute error. Compared to classical physics informed neural network, our model allows to generalize to different geometries and pressure source terms, maps. And against classical numerical method, our model could predict a solution 7 times faster. But then, of course, classical numerical methods are still more accurate and have been proven to be. So there are already been some similar models that have been trained, but only on small 2D meshes, and this is, to the best of the knowledge, the only network that is using a finite volume method. So further work should include training on patient myocardial meshes only, and more realistic pressure source term. And also we would like to see if our model could allow us to solve the inverse problem. Thank you for your attention, and please come see our poster if you have questions.
Thank you for the nice presentation. So now you can start asking questions if you wish. There's one over there. On the right.
Thanks for the nice talk. Maybe I missed that, but in the test set, do you use FFRCT simulation or just like you simulate some pressure maps?
No, so I'm using the model for myocardial perfusion, and here we do not use the FFRCT simulation at all. It's a different model.
Okay. Do you plan to do that in the future to better validate your approach?
Yes, of course, yes. So we could compare the two models. But here we just, with the neural network, here we just try to solve a part of the simulation. So yes, then the overall idea will be to replace the entire hemodynamic simulation, and then, of course, we could compare with the FFRCT simulation to see if we can validate our model. Thanks.
Thank you.
I have a question myself. So I don't know if you agree with me, but it looks like one limitation of the current method is the synthetic shapes that you generate, which are very smooth and maybe not representative of actual test data. Do you plan to work on this in the future, or?
Yeah, I completely agree. Yes, it's super smooth, and for sure, yeah, we already collected more patient myocardial meshes, and now we are able to train our models directly on those patient meshes.
On meshes extracted from patient data?
Yes,
okay.
From patient data.
Oh, another question here.
Yes, thank you for the nice talk. So if I understood correctly, you used position encoding of the vertices as input for your network. So have you thought about what it does to the rotational equivariance of your network? So if you rotate the mesh in 3D space, will you then still get the same pressure map?
Interesting. Yeah, no, we did not look at this, but yes, we should do it. We should look at this.
Okay, thanks.
We already talked about it, but yeah.
Yeah, in our group we're working on that, so maybe we can discuss later.
Yeah.
There's a question in your back. Yeah.
Thank you. Yeah, thanks for the very interesting talk. One extension towards the real data and shapes. On the errors you used, I mean, there are very quantitative errors used in this type of works. I was wondering if there are mistakes in terms of difference of pressure that are more important than others on the clinical use case. So meaning, are there big quantitative errors that we can do as a model without having a big impact on the diagnosis, and small errors that would actually be critical for the patient?
I'm not sure to have understood your question, sorry.
So if you go on the slides where you had the samples, yeah. So I mean, here when we compare the two methods, they make mistakes on different places in the mesh.
If there are more important...
yeah, are there more important spaces where we should not do mistake at all for the sake of the patient, and where we are actually, it's okay to make mistakes?
I think so. The main objective of the perfusion pipeline is to simulate perfusion map of the myocardium, and then clinicians have some thresholds in order to say if the ischemia is significant or not. So I think we should see if we can, even if we have some errors, we could still obtain, we could still predict significant lesions or not using our method. I think, does it answer your question?
And are they looking at all the
yes,
all the mesh?
Okay. Yeah.
Okay. Thank you.
Okay, all right. Let's thank the speaker again. So that concludes the session, and also very important for tonight. Allez les bleus.
Okay, we will move on with our sponsor event. So it's not time for the break yet. We have two presentations before the break. So one by Olea Medical and one by GE Healthcare. So we'll start with Olea. Okay, we have two speakers for Olea, Julien Rouillet and Habib Reba. So the floor is yours.
Thank you. Your kind introduction. So yes, we are two today. I'm Julian and this is Habib. I'm going to start the presentation with a more corporate presentation. Habib will take care of the rest of the presentation. So we are going to present some insight. Thank you. About the way we do AI at Olea Medical. Some numbers to start. Olea Medical is a 15 years old company. We are part of the Canon Medical Group since 2015. Please meet the employees at Olea. There is all kind of jobs. We are part of the research and innovation department, but there is also developers, sales, marketing, such the full jobs in the company. We have more than 10 dedicated medical applications. We focus on MRI, ultrasound, and X-ray CT. We do research, we do innovation, and we enjoy to work with public laboratories and institutions. As illustration, we participate in the Marvelous project. The aim of this project was to improve the analysis of images obtained by MRI for the heart and brain for optimal emergency cares. Olea developed the post-treatment tool. On the right side, you can see a non-exhaustive list of the institution which collaborates with us. I guess the main idea here is to say that Olea is not an island, and we need collaborations with laboratories and hospitals to make great products. So yeah, so the project objectives is to make something close to a radiologist copilot. The purpose is to improve the clinical workflow, and the result for us is to give to the clinician more time, to devote more time to the patients. We use a development strategy which consists in a user-centered approach. That means that we do numerous interviews with radiologists and specialists to understand the way they work and their needs. This is really important for us. During the development of the product, we do user tests to assess the effectiveness of the product with users to get their feedbacks and then modify the product accordingly. We would like to have this kind of wow effect that Laure Fournier described yesterday. We want a good end user adoption of your product. At some point in our work at the Research and Innovation Department, we need to develop frameworks for deep learning models development. So because we do products and we have regulatory constraints, let's say constraints, we must be able to regenerate specific model at any time and at particular points in the development. So we made specific homemade tools to support the complete pipeline of deep learning models. We do classification, we do detections, anatomical structure detection, segmentation of organs, and also image registration, multimodal image registration. Here it is an illustration of what we do, what we present to the clinicians. This is the interface of the neurovascular MR solution. UX, user experience team, made a great job. On the right side, this is some result of our models, which are embedded in the pipelines for this product. You can see vessel extraction, which is used for the vessel occlusion detection. Bottom, you can see the parenchyma segmentation and also a stroke lesion segmentation. Second illustration is for the breast solution, MR breast solution. As well, the workflow was studied precisely with the clinicians, and also some results: thorax and breast segmentation, fibroglandular tissue segmentation, and also we propose enhancing object detection, as you can see on the GIF videos. Now I let my place to Habib to talk about quality index.
Merci Julien. Bonjour tout le monde. So I will talk about the quality index, which is a shared project in the research and innovation team of Olea. More precisely, I will talk about the quantification of the uncertainty. So why Olea is interested by the subject? Well, for us, the main reason is to manage noise and other anomaly. Maybe you don't know it, but Olea is one of the first company that brings Bayesian estimation in MRI quantification to the clinic. You can see some example of our publication and event recently, since the first one is from this year. This is why we are very interested by the variational inference, since the Bayesian estimation, I mean the classical one, take a long time to compute, and our first test with the variational inference and the literature show some promising results in terms of computation time. However, if you already tested, you probably know that it's very complex to implement, especially when you want to create some hierarchical model or more complex probabilistic model. This is why for the moment we focus our work on the prediction of the error with the uncertainty. So there is three main ways to do it. I will not talk about the first one. I know it's very popular, but we didn't test it, so I will let it. But we made many tests with the second one, which I think it's the most popular one, the Monte Carlo dropout. And we made also some tests with the third family, which is interesting because it allows us to estimate the uncertainty with just one inference. So of course there is the variational approach, but we made many tests with the learning confidence estimate. So here it's one of our first tests with Monte Carlo dropout. It was a segmentation of the myocardial. You can see that we succeed to link the misclassification case with higher estimated uncertainty. So in this case, the misclassification are the error, which is our goal. However, all the methods that we test have some limits, and for this example, it was a model to correct the saturation effect on the arterial input function. You can see that for the Monte Carlo dropout, we failed to link the error to the estimated uncertainty, and for the LCE, there is some promising results since there is a range of the error which is correctly connected to the uncertainty. And this limit is a known limit in the literature. You can see here an example of an article. It was a segmentation task. They failed to link for the case of myocardial, for Monte Carlo dropout and LCE, the error, which are the red bar, the misclassification, to their confidence estimate, which is the inverse of the uncertainty. But forget this limit for the moment. Let's say we have a perfect algorithm, which in this case means perfectly link the error and the uncertainty. What is the best way to transfer this information to the clinic? Is a physician interested by this kind of map of uncertainty? Maybe not. Maybe he will be more interested by one single value, like the average, the maximum, or other singular value, with the threshold to say, yes, it's a good result, and no, it's a bad result. And more than that, is all the uncertainty of such a map relevant? I mean, you can see that the boundary presents higher uncertainty than the rest of the image, but it's a boundary. Of course, there is uncertainty. There is no relevant information in there. It's a region where the contrast is not clear. There is noise, there is a resolution issue. So, of course, we will have higher uncertainty. Probably in this map, the more informative region is here, where we can see that it's a clear error, and you can see here that the uncertainty is higher than the rest of the image. And why we are talking about that and about the limit before? Because for Olea, the main purpose of Olea is to bring research innovation to the clinic. And for us, from the point of view of Olea, the estimation of the uncertainty is a mature subject to bring to the clinic. However, we see some open issues, some open questions that need to be fixed. And for that, well, we need you. We need research. We need collaboration with you. So we are really open to collaboration with thesis, with classical collaboration. So please don't hesitate. You have our contact, and we are waiting you. Thank you.
We have time for one or two questions here.
Yeah, thank you for your presentation. For the vessel occlusion detection that you're applying, do you do it in CT or in MRI, and what's the like the detection process that you apply there?
I didn't get the last part of the question. Can you repeat, please? Occlusion?
Yeah, for the vessel occlusion detection process, which algorithms are you applying there? I mean, if you can disclose that.
Which sample we use, you say?
Yeah, which algorithm?
Which algorithm?
Yes.
I'm not sure I can give you this information, but it's segmentation of the vessel, first of all. And then for the occlusion detection, we used also, we used the classification. I didn't work on it, but we tried different approaches, classification, segmentation, and also object detection like fast RCNN or YOLO techniques.
Okay, thank you.
Sorry.
Hi, thank you. Thank you for the talk. I was interested in the Bayesian approach to quantify uncertainty. Have you looked at quantifying the sort of underlying MRI parameter using this approach? For example, diffusion-weighted imaging using Bayesian to estimate the uncertainty of the signal itself.
To be sure, you ask what we do with the Bayesian estimation?
Have you looked at using the Bayesian approach to quantify the uncertainty of the, say, diffusion-weighted imaging, the image protocol?
Yeah, it's probably interested for. Yes, with the EVIM model, you mean? Something like that.
Diffusion-weighted We can have an offline discussion.
Yeah, we can talk after, but we are really open. We have we explore many subjects in MRI quantification. So our main goal in the future, I mean, is to introduce the Bayesian estimation for all this kind of quantification. So,
thank you.
Let's thank Olea again. So the next presentation will be by Nicolas Gaugin, so for like GE Healthcare.
Thank you. It's a pleasure to be here. So Nicolas Gaugin, Director in Advanced Visualization at GE Healthcare. So I'll start with some introductory slides about GE Healthcare, and then I will share some AI use cases. So GE Healthcare is a leading global medtech with a revenue of $20 billion, with more than 1 million patients served annually. We'll not go through all the figures, but we have one important figure here is we have 58 AI-enabled medical devices that have been authorized in the US, so cleared by the FDA. And GE Healthcare is the company that has the largest number of AI medical devices. I will give some examples. So GE Healthcare is a global company present across the world. So you see many R&D sites in the US, of course, US, Canada, also in Europe, India, China, and Japan, and also lots of manufacturing sites and customer service. So we are divided in 4 segments. Imaging, of course. We are manufacturing CT scans, MRI system, also nuclear medicine. We have ultrasound, patient care solution, and pharmaceutical diagnostics. So a couple of slides about the presence in France. So GE Healthcare is present in France. We have a large site in Buc, near Versailles, in the Paris area. So almost 3,000 employees. Sorry, this is in French. But GE Healthcare is the first medtech employer in France. And we have, as I said, an important site in Paris area with more than 600 R&D engineers. And the area of expertise here in France is listed here. So we have a strong expertise in interventional imaging, in mammography, and in advanced visualization and AI. We also have other activities in dose management in Strasbourg and ultrasound probes in Sophia Antipolis. So we are in a medical imaging deep learning conference. So I will share in a couple of slides why artificial intelligence and deep learning is important for us. So I show here a picture of the famous UNet model. And I can tell you that most of these AI medical devices are using this classical architecture for segmentation. Why it is important? Because there are more and more data that is generated by these imaging systems. We are talking about 50 petabytes of data each year. An important thing is that the imaging acquisition system are improving over the years. And interestingly, it's also partly due to deep learning algorithm, because through deep learning we are able to reduce the noise, to improve the image quality, to reduce the acquisition time for MRI, for example. And so this in turn generates more and more data. And more data, more and more images. So it's, of course, takes a lot of time for the radiologist to review those images. And so that's why it's very important to provide to the radiologist like efficient tools, and in particular AI components, so that they can read images faster and deliver the diagnostic more effectively. So then I'll talk about advanced visualization. It's also known as AW for radiologists. So this activity is located in France. And we have a broad portfolio of applications, more than 30 applications that were developed over the years. Some of them have been developed more than around 20 years ago, so they are quite old. And they are covering all the space of radiology. So you have cardiovascular, oncology, orthopedy, neuroimaging, a lot of different applications for radiologists. I will take one example, which is the application that is called Hepatic Vicar. This application was released more than 10 years ago, at a time where we were not talking about AI and deep learning. So in this application, so that's an application for CT that is used to analyze the liver diseases. And at the time, the algorithms that were introduced in this application were not, of course, AI-based, but more using classical, traditional image processing, segmentation. So you might think that segmenting the liver is an easy task, but at the time that was quite challenging. So the type of algorithm that was used was atlas-based segmentation. In fact, liver segmentation is easy on normal cases, on healthy liver. But when we look at different diseases, you see that there are lots of challenges. And here are a couple of examples of the type of variability we can see on the liver on a CT scan, be it related to pathologies or treatment. So, for example, you have high densities related to the treatment, or hypo-intensities related to disease or lesions. So that's Hepatic Vicar is one of the first applications that we refresh with AI, and that's to give you an example how we can improve like liver segmentation using more advanced techniques such as deep learning on complex cases. So here you see a difficult case. We are not able to do the segmentation correctly with the previous method, but with deep learning we have a perfect result. Just a few other examples of AI use case in AW, Advanced Visualization for CT/MRI. We have today 9 medical devices that are using AI. That's mainly doing for segmentation, so first step of the workflow. But not only. So for example, here the first example on the left is spine labeling, CT spine labeling. Again, a quite difficult problem, in fact, with traditional image processing techniques that we can solve with deep learning. We have also several applications around vessel analysis, and also in the domain of oncology. On the right, you see the application that is called ProView for prostate cancer analysis with MRI, where we introduced prostate gland segmentation with deep learning. Some lessons learned about all those developments, recent developments in AI. So in my team, so we are working mainly on 3D imaging. Dealing with 3D is of course challenging. You have to consider that one single CT scan can take up to 1 gigabyte of data, up to 1,000 different images for a single scan. So there are a lot of challenges around inferencing time, performance, memory footprint. So we use a lot of hybrid approaches to reduce this inferencing time. We combine some classical image processing with deep learning, for example, to limit the area where we do the inferencing. Of course, a big challenge to annotate and validate a large amount of 3D scans. And again, here we are relying on traditional image processing to boost the annotation. And in particular, we are relying on the application that we have released over the years Like old application, for example, hepatic vicar, the first version of hepatic vicar was used to annotate lots of cases so that we can train a unit model to better segment the liver. Today, there's, the last point is there's no foundation models for slice imaging. There are some research, but it's the beginning of foundation models for 3D. That might help in accelerating the model development. It's important to note that today the models that are released are highly specialized and also very optimized. So somehow it's probably difficult to replace those models by foundation models, but they could help in the development cycle for sure. A few words about the data. One of the big challenges, of course, is that there are cases with, as I said, lesions, pathologies, anatomical variant, rare disease. So it's a bit like a long-tail distribution problem. If you really want to have super high performance, you need to find those cases with the current techniques and use them in the training process. It's important to note that we had actually limited success with data augmentation. Data augmentation helps when you have a very small training set, but when you have a larger training set, I think the boost that it gives vanishes a bit, and we have to maybe implement more advanced data augmentation techniques. So that's not easy, and that doesn't really solve the problem of the long-tail distribution problem, getting the rare cases. Another challenge is that I said the acquisition system are evolving with higher resolution, photon counting, etc. And so we need to refresh the databases for the training set, but also for the validation set. So models requires updates. A very high bar for success. There is a growing regulatory burden of proof. The regulators are asking more and more in terms of proof that the model works well and is reliable. And of course, we have to demonstrate that this is useful to the radiologists, which takes a lot of time and energy. And I think Laure Fournier mentioned yesterday the need to have those kind of multi-reader, multi-case studies. That's the ultimate way to demonstrate that an AI algorithm is really useful for the radiologist. And just to elaborate a bit on the regulatory constraints, here are the type of question that regulator will ask about an AI-enabled medical device. So different categories of question. Data sufficiency, they will ask a lot about do we have enough exams in the training set? Do we cover, that's especially true for FDA, they want us to cover, of course, US, so have cases from the US, and that's the same thing for China. The NMPA will require to have test cases collected from China, or at least test cases that are in China. Which is a challenge, obviously, because, of course, we need to cover the entire world. And also, if we want to claim vendor-agnostic AI, we need to cover other vendors, non-GE vendors in our case. There are questions about metrics and acceptance criteria. And typically, we cannot just say we have a dice score of 0.8. That's not sufficient. We have to really explain why dice score is correlated to the clinical benefit. And that goes back to the previous point. At the end of the day, we need to demonstrate that the radiologist plus DI has better performance than the radiologist alone. Truthing process, also, how do we build the ground truth? That's a very important point. And today, the requirement, in particular from FDA, is that we have to create ground truth from a consensus of at least 3 experienced radiologists. Again, that takes a lot of time to build this ground truth. And question about AI methodology, of course, making sure that testing data is independent from training data. And more than that, that the site that are used to create the test set is different from the sites that are used to create the training set. So that's my last slide. If you want to connect with us, we are, of course, present in social media and those different links. Thank you.
We have time for one quick question. If there's no question, well, Nicola will be there during the day, so you will have the opportunity to go and chat with him. And otherwise, please thank again all the sponsors of the conference. Thank you all.
Anything? Hello? Hello, everybody. Welcome back. And now, after this pause and the lunch break, we are ready to start with the third keynote speaker of MIDL this year. So we are very, very happy to have here with us Karim Lekadir, who is a ICREA professor at the University of Barcelona. And overall, he obtained his PhD from the Imperial College in London, and he did his postdoc in Stanford University. Now he's an ERC holder of a consolidator grant, working on how to apply AI on limited resource-limited settings. So actually, he will talk to us about the whole picture, or the title actually of his talk is The Whole Picture, Building Trustworthy AI in Medical Imaging from the Ground Up. So thank you very much, Karim, for joining us, and I think we are ready to start the session.
Thank you, Maria. Thank you for the invitation. I'm really glad to be here with you. It's my first MIDL, and first of many. I will be back. I enjoyed in particular the gala yesterday. It was really amazing. I heard there was a follow-up with a museum, karaoke or something. So I don't know how fit you are to listen to my talk. So I'll make it nice and easy. I will just tell you some experiences I've had over the last few years working on AI, trustworthy AI. So I will tell you some experiences in Europe, working in multiple European countries, then on organizing MICA in Africa this year. I hope you will be there. And doing AI in low resource settings, interacting with stakeholders. So I learned a lot from these experiences, for example, interacting directly with patients. And then developing guidelines for trustworthy AI. And there will be no deep learning. Well, I won't show any equations or anything like that. It's more about experiences and how to put into practice trustworthy AI. So first, let me tell you about my experiences in Europe and perhaps introduce myself a little bit. So this is Europe. This is where I was born, in a region called La Bourgogne. So when I went to study in the capital city of that region, in the Université de Bourgogne in Dijon, which coincidentally yesterday the Tour de France was there, if you're interested in cycling. Today there's a stage there, around there. Then I came actually to Paris, a long time ago. Back then I didn't like it, but I had a really good time now, so I'm changing my mind about Paris. Then I did Erasmus in Germany. Then I did my PhD in London. This is where I started doing research. And then I ended up in Barcelona and in Stanford, of course. So I would say, a European researcher. I had quite a few experiences across Europe. So now I'm in Barcelona. So I don't know how much you know of Barcelona. Here is Sagrada Familia, Camp Nou, and the university is in the middle here. Of course, there's a beach, so there's many distractions. But there are also reasons to work. We have a hospital really close by, Hospital Clinic. We work with them closely. And then there's another institute I want to tell you about, Institute for Global Health, and they're helping me with this research I'm doing in Africa in particular. So if you want one day to visit me, please write me an email. You're very welcome. So I work a lot with European grants. So there's a love-hate relationship with European grants in Spain. We love them because we don't have a lot of funding in Spain. But some people complain that there is a lot of administrative work. But I still really like them a lot, and most of my funding comes from European grants. And the reason I like them is because they look this way. By definition, you have to have institutions from different European countries, at least 3. That's the rule. And that changed the way I did my research, because suddenly I had data that was very diverse, that was from multiple countries. And that was not like this all the time. Huh? So for example, in this project, we have data from all these different places, and the needs are not the same. The needs for AI are not the same, say, in Bucharest, in Romania, than in London, UK. But before that, when I was doing my PhD, back then I worked with one institution. So there was a hospital called Royal Brompton Hospital in London, and it was walking distance, and I would go and get some data, and that's how I wrote my first journal paper on active share models, as it was called back then. A few years later in Barcelona, we did the same. We worked with one hospital, we extended it, we had something a bit more fancy, but still using active share model. But it was nowhere near what we can do now with deep learning. So in 2007, there was the ACDC challenge on cardiac image segmentation with MRI and also diagnosis. And the numbers went to the roof. The results were so good in that challenge that the organizers of the challenge, they titled their paper, "Is the Problem Solved?" And I thought it was. I thought, these are fantastic numbers. And coincidentally, they had data sets from one center, and it was Dijon, where I started my education. So they had really very good results. And then I participated in my first European grant, where we had data from Barcelona, Hamburg, but also data from Canada in that particular project, from Montreal, from McGill. And then we thought, well, let's do the same as in ACDC, but this time we'll use data from different hospitals and see whether we're getting the same. So we had 6 hospitals in 3 countries, and then we have 4 different vendors. And then suddenly the numbers were not the same. So big decrease in accuracy, lack of generosity, lack of robustness, all sorts of problems you can imagine. We encountered them. Fortunately, the participants applied all sorts of mitigation measures, data augmentation, transfer learning, domain adaptation, etc., that they managed to address many of these problems. It was still not as good as ACDC, but the bottom line here is there are solutions. When we know there is a problem, we can fix it. I think in our community we have very talented researchers, but we need to know that there is a problem. If we don't know that there is a problem, for example, a lack of generalizability or lack of robustness, then we deploy a tool, and then this could lead to problems. Let me tell you another experience in YouCan Image. This is on cancer imaging. We had data from different places. So we had data from a place called Olea, which is northern Sweden, from Kaunas in Lithuania, and which was quite different from the data we were getting from Barcelona and Pisa in Italy. So in Barcelona, for example, we have immigrants from different continents, from Africa, from Latin America, so it's multi-ethnic. In Olea, it's more homogeneous. So we started looking at problems of fairness. That's how I started working on fairness, and quickly we realized that there were problems on fairness, for example, in breast mammography, in particular with respect to breast density. So we realized that women with low breast density were overrepresented. Women with high density breasts, so typically African women, they were underrepresented, and there were imbalance and biases. We fixed some of it, but this is an open problem in my opinion. We tried to fix it with data synthesis. We took low density breasts, and through a GAN, we transformed them into high-density breasts, but it worked to a certain extent, but I think this is still an open problem. In another project called Longitools, here we had longitudinal data. So something we looked is whether data set that come from these places, whether if we build an AI tool, whether it continues to work over time. So what we did, we built a tool for diabetes prediction, and we checked whether it continues to perform consistently. And we found that there was a breaking point around March 2013, not 23. So this is a problem that you all know. It's called data drift. And so again, knowing that this problem exists, we can then fix it. So, but we need a holistic approach where we're looking at all these problems. So we could develop AI tools that are free of all these risks. From the same project, we looked at fairness for depression prediction, And here we looked at really a lot of variables. So we found that, for example, the models were biased with respect to sex, to income, so it's something we didn't do until then, to a certain extent to qualification. So if we apply certain bias mitigation measure, then you can fix these biases to a certain extent. Okay, so you can read more details in this paper. So at this stage, I had worked in a few European grants and I had encountered this problem, but then I asked myself the question, how does this work in other places outside Europe, in particular in places like in Africa? So I started thinking about the problem, and with a postdoc of mine, we looked at these journal papers for the year 2021, and we looked at every single paper. It was a lot of work. We looked where the data set came from, the country. And we were surprised to a certain extent to find that 95% of the data sets came for only 20 countries. And 133 countries had 0 data set in these journal papers. So this is a problem. So we're building a lot of AI, but actually it's really, really concentrated in a few countries only. So we don't know if these tools will be generalizable, whether they will be used in other settings outside these high-resource countries. So that got me thinking. So I started looking at the problem. I looked at the problem with radiologists, for example, how many radiologists are in different places. And there are certain regions, like in Africa, where there are virtually no radiologists. There are places where there are no specialists at all. So there's a lack of specialized workforce in those places, in particular radiologists. And then I looked at MICAI participation. I think this is for the year 2022. And we realized that, of course, there's also a huge imbalance. So a lot of papers, most of papers, and now I know it this year. So for MICAI, 2/3 of the papers this year come, I think, for 3 or 4 countries. So it's a really big concentration of research in a few places: United States, China, in Germany, in Europe, the UK, so, and Europe in general. Okay. And then I looked at, of course, the history of MICAI. It was organized everywhere in the Americas. In this place, Asia, Oceania, well, Australia, it was organized in 2007, and of course, Europe, and not in Africa. Okay, so I was thinking perhaps it's time to submit a bid. And there was another reason why I was motivated in this, and more personal one, which is that even though I was born here, I already told you, in a place called La Machine, because there was a machine extracting coal, my parents actually come from Africa, North Africa. So these are my parents. I always introduce them when I go somewhere. They are from this ethnic group called the Berbers, Kabyle in French. And so I thought, yeah, perhaps that's also a nice personal story. Perhaps they would be proud if I did it, brought MICAI to North Africa, to Morocco. But in fact, they were disappointed that I didn't bring it to Algeria. They complained. So, okay. So I thought, okay, I'll do it for me then, because really MICAI is my conference. I've been there since 2006. I go there every year. I've changed a lot over the years, but it's really my conference. It's become very, very big, perhaps, but I still go there every year, and I thought, okay, let's give it a try. So we submitted a bid in 2020 with these very talented people, in particular Julia Schnabel. She's the general chair with me. And yeah, with all researchers from all the continents, actually, including from Africa. And we said, okay, we want to go to Marrakesh, because Marrakesh is really nice. It has amazing places, amazing hotels. Morocco is beautiful. I'm trying to convince you to come to MICAI this year. Fantastic food. I hope you come. And it's also it's well connected. From Europe, virtually from any place, you need 1 flight to Marrakesh, and then from other places, perhaps 2 flights. So it's quite good. Another thing that I like about Morocco in general is the visa policy. They have quite an open visa policy, and we know visa is a problem Last year in Canada, it was really a big problem. There were a lot of colleagues that couldn't come, for example, from China and so on. So, for example, Chinese researchers don't need a visa at all to go to Morocco. That's quite good. And others, they can apply online. And, you know, even Joe Biden went there, and Angelica Merkel and Robert De Niro. So it's really a great place, Marrakesh. You have to go. So this is where we're going to have the conference. It's a nice little area. Something we did after we got MICAI 2024 to Africa, we created the Africai. So it rhymes with MICAI, but it means the African Network for Artificial Intelligence in Biomedical Imaging. And we have more than 700 members and from multiple countries in Africa, and we organize events all the time, online, seminars, summer schools, and so on. So we're trying to promote capacity building in Africa because we realize there's a lot of talent there, but perhaps not for AI and imaging in particular. This is perhaps where we could do something. So we put a lot of effort into this. Also, there will be a MICAI Meets Africa workshop, There will be also a few challenges with African data, pretty much the first time this happens. We have already a few accepted papers at the main conference from Africa. We have also health equity sessions, so we want to promote a bit more global health at MICAI. Okay. And having worked on MICAI 2024, the next step for me was to say, now, whenever I write a grant, instead of just having European partners, I will systematically try to add partners from outside Europe, from low resource settings. At the beginning, I remember my colleague was saying, are you sure you should do this? Perhaps the grants will not be accepted, because this is European grants, right? But every time I did it, the grant was accepted, actually. So I will continue doing that. So this is an example, Radioval, where we have 8 hospitals, 3 of them outside Europe, in Turkey, Egypt, and Argentina. And this is AI for heart failure, where we have 3 hospitals in Europe and 2 outside, in Tanzania and Peru. I'll get back to this. And this is the AMIX project on fetal ultrasound, where we have 2 sites in Kenya, one in urban site and one in a village. And let me tell you a little bit about this project and perhaps some preliminary results so you can see what sort of problems there are there. So they don't have obstetricians, simple. No one in those villages. The only thing they have are midwives. And I met a few of them, and they're really, really talented and passionate, but they need some tools to be able to diagnose problems in those places and refer those women to higher level of care, perhaps to hospitals when they have really any issues. And this is where we propose maybe to have an AI tool do that job and help them. Something simple with a low-cost ultrasound and with a simple system of scanning these patients, as you can see on the left. These are my collaborators in Kenya. Marlene Timmerman is an amazing woman. She was a Belgian senator in another life, but she spent most of her life in Africa, in Latin America, trying to help women there, and she set up an amazing center in Kenya. And in particular, we work in this region called Kilifi, which is really a remote region. You have to go with a 4x4. There are no asphalted roads. So we're trying to develop some techniques so these AI tools could be used there. And the idea is to say there are not a lot of data there. They don't have systems to store past data or anything of that sort. So you're lucky if you found a few hundred data sets. But in Europe, we have a lot of data. So the idea is, how do you combine this data set that is highly imbalanced, highly biased, in a way that it would be optimal for the local population? So that's what we will try to do. So if I give you an example of something we did in Africa, in this project at the very beginning, so we wanted to do automated plate detection, which would be very useful for midwives, so they know when is it that they detect the head, the abdomen, and so on. And this is a known problem. There are papers from all countries doing this, but not in Africa. So we thought, how could we apply this to Africa? Should we just apply an existing AI tool that we have in Europe, for example? Should we build a new one completely, but there's not enough data, or should we combine them? So that's what we did. We got data from 5 African countries, and we built a model from data from Spain, from Barcelona. And yeah, the data is really heterogeneous. There's a few data sets in Africa compared to Europe, and the equipment is different. So typically low cost equipment in Africa. And when we applied that Spanish model, it worked immediately in Denmark. Even though it's a different country, different population, it worked immediately. But it failed in all of the African countries. But fortunately, we know how to solve this problem in our community. There are transfer learning techniques, and then it worked. Okay, so again, once we know the problem, most of the time we know how to fix it. Okay, so far, right, through these European grants and grants in Africa, I already told you about problems of robustness we encounter, generalizability, fairness, longevity of the AI models over time, and accessibility to these AI tools in low resource settings. So the big question is, how much can we trust these AI tools in healthcare and in medical imaging? Well, it turned out there are other problems. So for example, a problem of security. We know that AI in medical imaging is prone to adversarial attacks, and sometimes in amazing manners. By changing a little bit, adding a little bit of noise, the decision of the AI tool could be the opposite. There are problems of transparency, this you all heard about. Sometimes we hear about these amazing AI tools, but we don't know much about how they were built and so on. Explainability, I thought at a certain time that this was a solved problem, but now I'm learning little by little that it's not solved at all, that it's really a complex one, that sometimes the explanations don't make sense. A problem of usability, so clinicians like AI or seem to think that AI will help them, but they have little training, little knowledge of AI. So there is a knowledge gap there. So problems of usability, and then all sorts of other problems that you hear in the literature, for example, of environmental sustainability. So this was a paper in MICAI that studied the carbon footprint of training deep learning models. Okay, another way to see that the AI tools are still not there is to look at how much of the research is turned into AI tools that are deployed and used in practice. So this website is really cool. It's maintained by the Academic College of Radiology, and it lists all the AI tools that are AI cleared, FDA cleared, sorry. And last time I checked, it was this number, 263. So not a huge amount compared to all the research, all the papers that are published every year. It's a reasonable number. But yeah, so it's only a few dozens. And the other thing that is important to say is that they are clear but not approved, which means cleared means they are similar to tools that already exist. Approved means they underwent a much more advanced validation. So that's not the same. If you look at this website, they give you all sorts of statistics, and for example, per organ. So a lot of them are in brain, and then brain hemorrhage in breast and so on. So you can have an idea of where are the gaps. I would say if you want to create a company, probably it's go to liver, prostate, something of this sort. Seems to be a gap there. But what's interesting as well, if you look at the colors, is that most of the tools are focused on quantification. That's the green color. So typically segmentation, detection, things like that. The red is more decision-making, diagnosis, treatment planning, and there's very little of red. And the reason is quantification is low risk. Segmentation is low risk. You could have a tool that does automatic segmentation, and then the radiologist could check visually if it's correct or not and fix the problem. So even if the AI tool is not robust, is biased, the radiologist has a mechanism to to verify the quality of the AI results and fix them. But if you have these tools that we hear of all the time in the media, no? But breast diagnosis or coronavirus diagnosis or skin cancer diagnosis. Well, these are very nice tools to read about in the news, but they're high risk and a lot of them are not used yet in practice for all the reasons I described. So what's the next step? So let's see what happened in another area, not in AI. So for example, in the world of vaccines, how does it work there with the concept of trust? Do we trust these vaccines? Some don't, like this guy, if you know him. I put a lot of sports references because I'm a sports geek. But okay, I respect him in a way because he stopped playing tennis for a while. He's like, no way I'm getting a vaccine. So that's quite impressive. But then he won the Australian Open the year after, so he was fine. But actually, really, even though we heard a lot of complaints, etc., the reality is that if you look at the numbers, it's impressive. Coronavirus was in 2020, and then within a year, we went from 0 vaccines to billions. And there were some countries, very quickly, they had pretty much the entire population vaccinated, or most of it. Yes, probably there were some issues, as one would expect, but in general, they were safe. And the reason is because they're not built in a random way. There are guidelines that people follow. And these guidelines are approved by different organizations. And you cannot skip certain steps. You have a number of steps. And typically the researchers, they work on these vaccines, they follow these guidelines. Even when the vaccines are totally new, for example, with the mRNA that we had. Still, because they follow these steps, in particular steps 6, 7, and 8, they are reasonably safe. You can tell that scientifically that they are safe. So can we have something similar, perhaps, for AI? Let's see in other fields. So let me show you the FAIR guidelines. How many of you don't know the FAIR guidelines? Just an idea. Never heard of the FAIR guidelines? Okay, cool. Let me tell you about the FAIR guidelines. If you don't know the FAIR guidelines, that means you never applied for a research grant in Europe, the Horizon Europe. Because you're obliged to comply with these guidelines when you apply for European funding. So these FAIR guidelines are guidelines that you should follow to manage your data. So you have a new data set. You need to follow these steps so the data becomes findable, accessible, interoperable, and reusable. The reason they introduced this is because for a very long time, people were acquiring data and they were managing them the way they wanted. It was the jungle. And so typically, either you didn't know that the data existed, you just sat in a computer, or you knew but you couldn't access it, or you could access it but it was in a format that you couldn't use it, and it was not reusable for other reasons. So they said we need now to have this. And the paper in question is highly cited, and now it's an obligation to go through this. And they give you certain steps on how to do this. The first time I worked with this, I said, what is this? It seems so complicated. But once you did it once, it's not actually. And then it's great because your data set is findable. People can find it. They can collaborate with you. They can reuse it. They cite your paper. And we do this to a certain extent also in our community. In the grand challenges, we do this. But there is a more advanced way of doing it and a more standardized way that this community of researchers put together. And there's a website. You can go there, and they explain you how to do it. Okay, so can we do something similar? And so that's what we tried to do. with support from the European Commission. Actually, they really pushed us to do this because they're interested in these sort of guidelines. So we contacted all sorts of people around the world because coming up with guidelines, you need to do this in a consensus manner as much as possible. So we invited all sorts of experts, and it took us 2 years of work, a bit more actually, to work on this. So it's not easy because there are disagreements and we don't know exactly how to do this. And perhaps this will evolve as well. I will show you something, but it will evolve over the years, but we have a starting point perhaps. So the way we did it is we did a literature review in depth. I will show you some results. And then we collected ideas of guidelines, feedback, people voted. So there was things where we disagreed and we discussed them, we organized online meetings and so on. And then this led to 6 consensus guiding principles, like FAIR, but 6 of them, not 4, 6. And then consensus best practices, 30 of these different recommendations, and then practical step on how to implement them. So for the literature review, we looked at many things, but in particular, we looked at biomedical ethics. So we wanted to make sure that the AI tools are ethical, and ethical AI and trustworthy AI are very much interrelated topics. So biomedical ethics, they have these 4 principles. So whatever you develop has to be to bring good for the patient. It should not harm them, it should keep them free and autonomous, and it should be fair. And then this was extended. So this was biomedical ethics, and then there is AI ethics, which is a bit different. In AI ethics, we have additional principles. So for example, confidentiality, right to life, equity, and right to information. This is something really specific to AI as well. And we did this work of also looking whether there is a correspondence between trustworthy AI and ethical AI. Indeed, there is. If you look at all these different principles that we talk about, generalizability, it's related to a human right, a right to equity. Robustness, right to safety, right to life, because it's not going to kill you if it's safe, right? And so on. Explainability, right to information. So this right is actually in ethical framework that exists in Europe, and so on. So from this, we did a literature review, and we came up with all these different requirements that people think are important for AI. It's a lot of them. So we had to group them. We grouped them this way, actually. So we came up with 6 clusters, more or less. Safety and robustness and reliability, they're all sort of interrelated, and so on. Huh? And then from that, we chose a letter from each, and it was perfect. Now people can remember it. Future. Yeah, so this was what we gave. We said, okay, the FAIR had 4 principles, we have 6, but it will help us structure our thoughts. So now we need to focus on these 6 dimensions, and we need to come up with best practices with recommendations, which is what we did. I'll go straight to the result to tell you that we got 30, and we ranked them chronologically. So we said, okay, now at the design phase, this is how you should build an AI tool. This is step 1, step 2, and so on. The first thing is to engage interdisciplinary stakeholders. So if you want to build an AI tool and see it one day in practice, we think that this is key. And we don't always do this. Perhaps we talk sometimes to clinicians, but what we need to do is something a bit more comprehensive, talk to patients, perhaps to ethicists, healthcare managers, and so on. And we did this, and I can tell you it's really different. It really makes sense, and it makes a big impact. And then once you engage stakeholders, you can define the requirements, but not only the clinical requirements, but also try to understand the variations in the data, the sources of bias, perhaps whether there is a need for explainability, but what type of explainability. All this, instead of us deciding as engineers, say, this is the explainability method I should apply, perhaps we should have this dialogue, and perhaps the clinicians and the patients should tell us what type of explainability they want, etc., etc. Investigate the application-specific ethical issues. I will give you an example. and so on. And then at the development stage, we have these 5 steps. And really the only steps that I was familiar with before was these 2 steps that I perhaps apply to a certain extent all the time, which is the coding that we do. That's best practice number 14. But even that we didn't do very well. Typically, we build a model and we looked whether it's robust, but we didn't look whether it was fair. No? Whether here what we recommend is to look at implement measures against all the risks, because we can't leave a risk unaddressed, and so on. In the validation phase, we need to define an adequate evaluation plan. I'll get to it. Evaluate all these different dimensions, leave nothing to lack, and that's why I called my talk the whole picture, because we need a holistic approach to this, and then document everything. And then at deployment phase, there are things like quality control and periodic evaluation and continuous learning and things like that. So let me go through them. Engage interdisciplinary stakeholders. So let me tell you about my experiences. But first, let me just tell you that each of these best practices we then subdivide into practical steps, because what does it mean engage interdisciplinary stakeholders? How do you do this? Well, concretely, first you identify the stakeholders that you need to engage for your particular tool. It could be a nurse, it could be a GP, it could be an ethicist, because you're unsure. Perhaps you're going to use data from children. Okay, I need an ethicist that is specialized in pediatrics. So identify the stakeholders, tell them about the tool you are building, but tell them about AI. Some of them don't understand what is AI. So you need to provide some information, train them a little bit. Then talk to them, have communication channels. I will show some examples, perhaps co-creation meetings, and then analyze the results to understand a bit more what you need to do. So let me give you an example. So this is in project AI for heart failure, and we engaged the European Heart Network. So this is a patient organization, the European Society of Cardiology. So this is a professional association. CE Plus is a company specialized in AI regulations. And then these 5 hospitals, 3 in Europe, 1 in Peru, 1 in Tanzania. And we met physically twice, 1 in Brussels, 1 in Lisbon. And literally we talked about all these problems, sometimes all together, but sometimes we put together these small focus groups where they would go in a corner and talk about a specific problem. We did the same in Kenya for the other project. And as I was telling you, we had to go far with a 4x4, but we got there, we met the local population, and it was an amazing experience. And we needed translators to be able to communicate, but we learned a lot from having this conversation about how these tools should be built and what are the concerns that they have, in particular ethical concerns. But you can engage stakeholders in other ways. You can do it online. So we use these tools called murals that perhaps you know about, where people can write down ideas and discuss things together in this environment. So what is the result of all this? So for example, define intended use. So this is a typical mistake that we do in AI, I think. If you want to know how you should build an AI tool for secondary risk prevention of heart failure, the way I used to do it is talk to the clinicians, because they're the experts. And they told us, well, we need to predict change in cardiac function, risk of myocardial function, risk of mortality. Because if they know that this person has a high risk of mortality, they will do something, change the diet, give another medication. So it makes sense. That's it. End of story. Let's build this AI tool. But when we pushed ourselves to talk to patients, we brought them, we sat down and started talking to them, we realized they want something different. So this is what they want. They don't want to know if they're going to die or not. That's absolutely not. They're not interested. They want to know what is the risk of fatigue, what is the risk of back pain, things like that, of hospital readmission. So if they know by taking another medication or improving their adherence or improving their diet, they will be less tired, have less back pain, for them that's really important. Another example, define sources of bias. Same mistake. We assume that it's sex, age, socioeconomics, and ethnicity. And we said, that's it, end of story. That makes sense. We talked to our colleagues in Peru, and they told us perhaps ethnicity, yes, we are a very multi-ethnic society. We have Native Americans, we have black people, white people. They even had a president whose ancestor was from Japan. They have a small Japanese population. So yeah, but they were not really convinced. From their experience, that's not what's really important. So they told us, actually, if it's possible, we'd like to study something else, another source of bias. I don't know if you guys could guess. Where was it? Not these 4 factors. Have you ever been to Peru? If you're not from Peru or Latin America, perhaps, I would have never guessed. That's why you should never assume, you should have this dialogue. So what they said is altitude. So altitude is posing a lot of problems to these cardiologists in Peru, because it's a country that goes from sea level to 5,000 meters. That's why tourists struggle to visit Peru a little bit, because if you go to those places, you have to have oxygen. But people live there for centuries, and they're totally fine. But their lung capacity is huge, the heart is different. And they said, this is clearly a problem for us. And by knowing this, we were able to anticipate and collect the right data and so on. So having this conversation is very important. Same thing for explainability. Before coding anything, you need to show them the different approaches and talk to them and see what is it that they prefer, what is it that more appropriate for their problem. Another thing is to identify the ethical risks. So this is something that we did in Kenya. So we said, with AI, we will do something that an obstetrician would do in Europe. So an obstetrician in Europe would check the viability, number of fetuses, the sex of the fetus, fetal weight, position, and so on. And through this conversation, talking to the local population and so on, we realized that there was a big ethical issue in doing this, which we haven't solved, but at least we know now. I don't know if any of you can guess what is the factor here that posing problem. Sex, huh? Yes, so apparently there's something called selective abortion. So if they know it's a girl, some people will say, let's abort. So now we have a dilemma. We could say, well, it's easy. Let's not add it to the AI tool. But then if you don't, you create an inequality. You're saying European women have the right to abort whenever they want, but not certain African women. Or at least that's what came up from the conversation. Some women say, we have the right also to abort. There's no reason why the abortion for us is sure, but selective abortion is problematic. So I don't know. I don't have a solution for this, but I'm just telling you, at least through this conversation, we learned that there was this problem. Okay, I'll try to finish in 5 minutes. Okay, so then you come up with these requirements. The development part, this is important by knowing that altitude was a problem in Peru, so now we can collect the right data. And then implement measure against identify AI risk. This we know how to do. We put some steps, but there are so many techniques to solve these problems once we know they exist. For validation, yeah, we need an adequate evaluation plan, and then evaluate and document. So for example, for the evaluation plan, I will refer you to some papers. So for example, the first one, Metrics Reloaded, gives you recommendation on which metrics you should use depending on the problem, the type of data, and so on, number of classes, etc. So it's a nice, really nice piece of work that this consortium have done. There are other papers to focused on fairness, others on explainability, to tell you which criteria, which metrics, and so on. So you can define an adequate evaluation plan given your problem. For explainability, same thing. We put together a number of steps, and there is a lot of literature on this as well. For documentation, we also recommend to put some effort into this. This is something that we don't do a lot. We describe our tools for the research community, but not for the clinicians and patients. So it's something I think we should do in the future. Finally, deployment. That's very important, of course, because it's not finished. Now you have a validated tool, but you need a periodic auditing system, for example, something of this sort that can detect data drift, that can look at performance over time, do some time series analysis, and so on. Okay, so what does this all mean for you? First of all, I would say these are recommendations. So you can follow all of them, some or none. It's just some recommendation that a bunch of people came up with based on different experiences in all continents. We think that they could be helpful. But I should say that, for example, personally, I'm not going to use them all because I'm a researcher. I don't have a company. I'm not building commercial tools. So perhaps I don't need all of them. Instead of 30, I will follow 15 or perhaps 20. But perhaps one day those tools that I built with 20 best practices, one day I want to then commercialize it, and I'm close to have to following the whole process. So following some is already very good, I think. But it's also good because it helps you develop in good habits. So for example, the habit of talking to stakeholders, in particular to patients. Try it one day to talk really to patients directly, and even psychologically, the way you do your research, I think it has an impact. And to remove pre-assumptions, like the ones I described on biases and so on. But really the main thing is this. If you are interested in transferring your tools one day, by the time you retire, to be able to say, I did something that was used in the clinic, then I think following these recommendations can be very useful. And in particular, if you're interested to commercialize your tools, create a company, then that would be very useful. And I hope it will give you some ideas for research, because when we look at that table, which you can check in the paper, there are some gaps. Some things are well developed and others we still need more research to develop them. Huh? So this is the website of the consortium, and it has a link to the paper. I think we're updating it actually this week, so there is a new version of the paper, because every year it will change. And that's it, I think. So I just to thank the funding bodies, MIDL, of course, MIDL for inviting me. I had really a great time. It was 24 hours exactly, not an hour extra, but I had really the best 24 hours in Paris since I know Paris. And I want to just thank my lab. They did all the work. And thank you all for your attention.
Thank you very much, Karim, for this very, very nice presentation. We have time for some questions. So, question from the audience? Yes, there is.
All right, can you hear me? Okay, so super nice talk, Karim, and also bringing MICAI to Africa is great. You are putting together also the equity track in MICAI. That is also great. I was wondering one particular problem. It's basically when you are looking at the peer reviewers, you still have a pool that is primarily the same pool that is submitting papers historically in MICAI, right? So how do you incentivize that pool to think beyond the obvious question about technical novelty to reject or accept a paper and think what else is there?
It's a very good question. I wish I had the answer. We thought about it a lot. I hope we will get there. So this year we thought we're going to have some submission from Africa, because we really worked very hard to promote that. We even looked for sponsors that will pay the trips of those African researchers if they get their paper accepted. So we did a lot of work. But then we said we cannot change the system. They need to go through the peer review. That's fair. So that's one thing, is through this health equity. So they go to that track, and it's a different track. There it's a bit more application focused. So perhaps that's one way to do it. But still, our experience is that most African-led papers were rejected. Only few were accepted. We were quite disappointed, I have to say. but it's good. We understand, we now realize there is a problem. Of course, you can't, there are two individuals competing, one from the US, it's been in the game for forever, and somebody, it's their first time, and they barely have computational resources, and it's really, it's not the same race actually. It's a competition, but not with the same weapons. So, as I said, perhaps having separate tracks, parallel tracks, things like that to promote, but still the quality has to be there. Even for that track, the quality was not enough. And then do capacity building. So that's why I showed you that Africa network that we created, and by the way, I can tell you that we will apply for it to become a special interest group within MICAI. So we'll receive a bit of funding from the MICAI Society, so it will continue. Because we started something and we have to continue it. We hope that every year there will be more and more African papers at MICAI. And then one day perhaps it will become a chapter, no? Like there are conferences, so, but we're still not there. But yeah, so we're trying certain things. But if you guys have ideas on how to improve this, the review is really complicated, I've learned. It's a very complicated topic. There's no perfect system at all. But yeah, thank you for the question. It's really, really interesting one.
Can you hear me? Yeah. Thank you very much for the nice presentation. I have two short questions. The first one is about the checklist and guidelines. So actually, there are multiple checklists like claim, clear, tripod, future AI. And with this regard, are there any guidelines or recommendations or like any strategy how to follow them, how to navigate within all those available checklists?
Yeah, so what we did here is different from those checklists. They are checklists to write papers on how you should report the result. It's only about that. Here it's something, it's about the whole process from design to deployment, to validation, to deploying the tool on how an AI developer should go through the process. So these are two different things. In what we did, I would say there are also papers recommending things. The only difference is that we did it through consensus. Now, regarding the reporting guidelines, should you use claim or should you use tripod? I would say some of them are specific to imaging. For example, claim. So if you're doing medical imaging, perhaps claim. And then within medical imaging, there are reporting guidelines for radiomics, no? Yeah. So you can sort of go, some of them are focused on diagnosis. I agree that perhaps it's too many, but I would say it's better to use any than nothing, that's for sure. Yeah. So any of them would be okay, I would say.
Thanks. And the second question would be, how flexible could be this framework with these checklists? So for example, is it expected to be expanded somehow, or what is the procedure to introduce new changes? Like, should it be done via gathering the whole consortium, or I don't know?
Yeah, it's a very important question. We need to set up a system. So we have a website, perhaps we're going to set up a mailing list or something, and we're going to organize events, and we'll try to collect feedback. Because things will change. That we are 100% sure, and by the way, that's true of any guidelines. They change every few years, no? Like clinical guidelines. Pretty much every year there are new clinical guidelines of this. Well, they change a bit. So there's no reason. We should perhaps ask those committees how they do it and do something similar. But it's a very important question indeed, yeah. Thank you.
Thank you.
Yes, we have a couple over there.
Hello, and thank you for the inspiring talk. Do you see, maybe as me as well, any contradiction between the fact that the collection of the personal, sorry, yeah, it's gonna be better. Do you see any contradiction between the fact that the gathering of the personal data is quite restricted and the presence of these unexpected biases?
Yes, that's a very important question. So, yeah, there it's, in my opinion, building an AI tool, above all, it's a risk balancing exercise. No, I think one of my colleagues, that's what he taught me. You've got different risks and you need to balance them. So you have a risk of re-identification, that's a risk, and then you have a risk of bias. And you need to find a balance there. And it's not only this, for many other things you have these types of dilemma. Personally, I would say that the risk of discrimination is a bigger risk. Perhaps we can build systems to still keep the data secure and private while providing extra information. Perhaps we can do that, and I think we can do that. We've now learned how to do this. There are all sorts of techniques, federated learning, differential privacy and things like that. But we cannot have AI tools that discriminate about certain subgroups, in my opinion. So perhaps in this, but it's not easy. Huh? Sometimes these risks, there is a conflict and you don't know exactly how to do it. That's a very important question.
Yes, sorry. Thank you very much. Very interesting talk. I have a quick question. So I haven't been so long in the game, so you can correct me if I'm wrong, but I feel like the subject of fairness and the data from smaller communities is not well represented. It's been in the air for a while already. At least 5 years ago, I know people already started talking about it. And so my question is, why do you think this is still there is not a lot of effort to solve it? And also whether this problem is specific to medical AI now and that in other applications it's better?
No, it's a very, very interesting question. Indeed, there has been a lot of progress and there are many techniques to fix the bias. I think the reason it's still there because it's relatively new. I think that's one of the reasons. We don't have actually data. We don't have a lot of data to study this. I mean, the number of times I asked my collaborators who gave me data sets, can you give me the sex or the age or something, and they say, oh, we forgot to put it there and it's too late. So a lot of this data, if you go to the grand challenges, for example, you will see that most of them don't have this protected attribute, so you can't check if there's fairness or not. That's why it's important to have these best practices, because you can learn to try to identify the sources of bias and then learn to collect the right data to be able to analyze the thing. So it's not a technical problem. I think technically we've improved. There are still problems of data imbalance. That's something that we need to fix at the data collection level. Yes, so in skin cancer, the data set that we have is overwhelmingly white population. So it's difficult to have a fair AI tool in those conditions, even if you have the best techniques. So that's why we're still working on it, because it's really, we're still early stage and there are other things that we need to solve beyond the technical problems, which we are solving to a certain extent. Thank you.
Thank you, Karim, for a wonderful talk. I just wanted to react on the element you presented on presenting the sex of the babies to parents. My opinion is that the knowledge is not what causes the problem, it's what people do when they have the knowledge. And we can learn a lot of what happened in China about this very issue, because they have, I mean, I'm not Chinese, so I don't want to say something too politically incorrect, but they have had an enormous sex ratio imbalance in the past, all the way to 100, the normal ratio is 106, so 106 boys for 100 girls, normally. In China, they went all the way to 147 for a third child, which is enormous. And so they discovered, they also, you can say for the Chinese, that they have a strong way of, and strong capability of implementing policies, right? You could say that. And what was discovered is that actually policies don't really matter. What matters is education. They saw this ratio decrease steadily as the ratio of education increased. And so there's a lot to understand from that. And now the good news is that the ratio in China is 110. It's not quite normal, but it's much better. And what happened also is that because of this ratio carried over to the people became adults, the status of women increased in even in the remotest, most rural part of China. And I don't know if it's a good idea a good way to do it, but it's good news that things are not fixed.
Thank you. It's interesting that you commented on this because I remember we had exactly that opinion when we discussed this. Some people said we should keep it as it is. We should provide that information, but we should perhaps provide education and increase literacy on what to do beyond after you have that information, that knowledge. But it was really a difficult conversation. There were some people in the group that said, if you include sex, I'm not part of the project anymore because I know what's happening after that. So it was really an emotional discussion almost about this topic. It's a very sensitive one, and we haven't solved the problem. But yeah, thank you.
One more question, yes.
Thank you for this interesting talk. My question is about like the overall concept of how knowledge is produced, and given that like AI, I mean the field of AI is growing and like AI research is actually progressing and the knowledge is being built through, knowledge production actually has its own ontology, has like the social concept of how knowledge is produced, and then there is language also that plays a huge role in terms of knowledge production. So when you're talking about like bringing in community from Africa and all, like how do you actually democratize this process where the ontology and basically the social production of knowledge is actually not limited in terms of like the European people actually building that whole hierarchy or like the structure of knowledge production, but it's also including like people from other communities. And going back to Anirab's point around getting in more people involved in like MICAI, I mean, scientific writing is also like, I mean, it might be a naive thing for us, but like for a person coming from a rural community in Africa or maybe even in India, might not be knowing scientific writing itself. So he might be having like really innovative ideas, but like in terms of scientific writing itself, he might be poor. So as a community, how can we think about like when we are actually getting in these people to produce and basically write papers and bringing in new concepts and ideas, they're not limited by like such by language or by scientific writing, are not barriers for them.
Thank you. This is an important question, and we experience the complexity of it. So we would like to. There's very little in AI for medical image, for example, in Africa. So clearly we need capacity building. There's no other way, and it does make sense that researchers from Europe, for example, from America, from Asia, would help in that process for capacity building. But it's true that we had people that were concerned about this because the capacity building is not coming from Africa itself, and that could be an issue. I totally agree. What we are trying to do is so we're aware of this, and what we're trying to do is progressively give more responsibilities to the African researchers. So it's, them organizing things. That's what happened with deep learning in Daba. I don't know if you guys know deep learning in Daba. If you don't, I would recommend that you have a look. So it's a deep learning community in Africa. It's the deep learning community in Africa. And they started this way, really. A lot of it came either from Europe or from Africans in Europe. But little by little, they did, because I think their mottos were for Africans by Africans. And because they were aware of this problematic, they anticipated from the beginning, and they put together a system so little by little the capacity building was transferred to the local population, and I think it worked for them, and I think we should do something similar. I'm actually interested to talk to them to see how they did it, but it's a very good point indeed. Thank you.
Okay, thank you very much, Karim, once more for this very, very nice talk.
Thank you.
And now, after all these discussions and the closing of the keynotes that we try to highlight discussions about how to apply all the algorithms we are developing to low resources countries, to clinical practices, and how to evaluate them properly. Now we will continue with the session on foundational models. So, yes.
Oh, hello, hello. Hello, everyone. Welcome to the session on foundation models. My name is Tal Arbel, and I'm here to co-chair along with
Ismail Benayed.
So without further ado, we have we'll just ask our first speaker to come up. Okay, so the first talk is about data usage and citation practices in medical imaging conferences, and here to present the work is Theo Soulget. Thank you.
So hi, I'm Theo from the IT University of Copenhagen, and today I will present our work on data usage and citation practices in medical imaging conference. So this work was supervised by Veronica Schepliger, also from ITU, and by Caroline Petitjean from the University of Rouen. So nowadays, the evaluation of models heavily relies on publicly available datasets used as benchmarking. And while this could be a nice thing for a fair comparison between different models, we question the effect of the diversity, or more precisely the lack of diversity, in research paper when selecting the datasets. A gap has been observed, as we saw during all these talks, between results in research by AI models and their adoption in clinical workflow. And we hypothesized that this could be partially a result of a sort of overfitting of research on these datasets. So we wanted to evaluate the usage to see if some are more popular than others. And while this seems like a straightforward thing to do at first, we'll see that it turned out to be not so easy due to some difficult elements, like this one, for example. So in our paper, we present a pipeline to collect citations and mentions of datasets in a research paper from MIDL and MIDL between 2013 and 2023. And we also developed an annotation tool for PDF, and both the pipeline and the annotation tool are fully open source, so that we can potentially extend our study to other fields of application. So I will first present like an overview of this pipeline. The main idea was to have, as I said, a tool easily extendable to other venues and datasets. So we relied on public APIs and open source tools. We can divide this pipeline in four parts. After defining the venues and datasets to be analyzed, we gather the information of the papers. Then we try to collect the PDF of the full text that we convert into a format more easily parsable. Finally, we try to detect dataset presence, mostly through regular expression matching, and we assess the efficiency of our tool thanks to our PDF annotation tool. So I will now present the first source of data for our work. It's OpenAlex. So OpenAlex is an open citation index tool. It's basically an API gathering information from multiple sources, such as Crossref, the Microsoft Academic Graph, or Archive, for example, among many others. And it standardizes this information. We evaluate other alternatives for this part, such as Open Citation or Semantic Scholar, but we concluded that OpenAlex was the best solution as it provided more information or had a better coverage of the papers included in the API. I have to mention that when searching for papers information, maybe the most famous thing is Google Scholar, but there is no API to collect data from it. So the data from OpenAlex looks partially like this. We were interested in the abstract, the reference in the paper, and the link to the full text PDF. As you can see on the left side, the list of references are already computed by OpenAlex, and each paper in the API has a unique OpenAlex ID. So all we have to do is to make a matching between the dataset IDs and the IDs present in the papers. On the right side, you can also see how we can access the full text PDF through OpenAlex with a link, but it's not always possible. So to deal with this issue, we also added the possibility to have an additional scrapping tool to gather PDFs from other sources. It was especially useful for middle papers, as they were poorly documented in OpenAlex API. To be more concrete, we defined a scrapping tool with Scrappy, but in the end, any external source of PDF can be used. It doesn't need to be automated at all. So now that we have gathered all this PDF, we have to transform it into a format more easily parsable. And to do it, we decided to use Grobid, which is a library to convert raw documents like PDF into parsable documents like XML. And it works especially well for scientific documents. So it was the perfect tool for us. Grobid extracts the information thanks to a cascade of models. So first it divides the paper into main areas, like title page, the body, footnotes, or the reference section, for example, and then apply some specific models to extract and restructure the information into an XML. So again, this is an example of the data we obtained from Grobid. And the main point here is that the XML conserves the structure of the PDF. So as you can see in the first red box, you have the beginning of the introduction section. And in the second red box at the very bottom, the beginning of the method section. It is very important, as we believe only mentions in relevant parts of the full text are important, such as the method, data, or result part. So we only collect mentions in those areas of the paper. So now that we have all this data from OpenAlex and from Grobid, as I said, we apply those regular expressions to search for the dataset's name, some aliases, or URL in the papers. Then we wanted to evaluate our tool, obviously. So to do that, we need to annotate some PDF, but we couldn't find the perfect tool to do it, as some other alternatives like Target and LabelSeed that you may know had some major limitation. So for example, the conversion from PDF to raw text for Target, which makes it harder to read, and the lack of free features for multiple annotators with Label Studio. So we developed our own annotation tool with Streamlit that allows for multiple annotators, keep the PDF format, and where you can also assign papers to different groups to ease the distribution of work among the different annotators. Now that we have a more clear view of the pipeline, I hope, let's talk about our findings. But first, I wanted to show why we needed such a quite important process in the first place. In the beginning of this presentation, I talked about dataset presence, but this presence can take very different forms. First, looking only at citations, maybe the one you have in mind for datasets is the first example, the most classical one, where you mention the dataset's name and then cite the papers. But you can also find citations that don't mention the dataset's name. And in our study, it was a problem because, as we want to assess usage, it was mostly the case for a paper that exemplify a statement in an introduction, and we're not really using the datasets. And you also have sometimes some bad citations, like in the last example, where the author only cites the link to the datasets and not the proper papers as asked in the dataset guideline. Same goes for the mention. So we had in the previous slide the classic mention, but you have also other possibilities, as we saw in the first slide of the presentation, with footnotes, with a link to the dataset. But you can also find some name in specific structure, like figures and tables. We analyzed further these different practices and found three main groups. The first one is what I mentioned before, the only cited group, so paper that only cite the dataset paper and not mention the name. And it's a problem because they're not really using it, as we discovered, and they represent more than 25% of the papers in most cases. So these figures show the percentage per group divided per dataset and per venue, so middle and MIDL. But we also have the reverse problem with the only mention group. So papers that only mention the name or URL of the datasets, but are not citing the paper or are it not properly. This is also a problem, as we often use the citation count to assess the popularity of datasets. But if we are not citing the proper papers, then it is not detected. And it represents more than 15% of papers in most cases also. And finally, we have the cited and mentioned group, which is sort of like the best case scenario and what we should go towards too. So it highlights the differences of practices and the lack of standard way to acknowledge and cite datasets. So now let's compare datasets together to see if some are more popular. So we selected 20 datasets, 10 for segmentation and 10 for classification for different organs. And we selected multiple for cardiac segmentation and chest X-ray classification to also assess the diversity for a similar task. Here you can see on the figures the cumulative count of citations in full line and mentions in dash line for some selected datasets that highlight our findings, but our first findings is that on the 20 datasets we selected, most of them were actually almost not present at all in the papers. So this shows the concentration of research on few datasets in the medical field that has been shown in other field of application before. But we can also check for a similar task, and in this case we can also see a lack of diversity. So for segmentation dataset, for example, we saw that BOTS is by far the most used dataset in our papers, but we can also actually see that ACDC and MNMs that we saw before have also very different numbers. So ACDC that was released before and had already high numbers is still very highly used and mentioned in papers, while MNMs that is released afterwards is already stagnating. There is some limitation, however, to this pipeline. So first, we only track citation to papers, while some datasets are only released on particular platform without a paper, and our pipeline won't work for them. Also, mentions could be affected by some homonyms, and funny findings we had during our study is that ACDC is an acronym used by 3 different datasets, and 2 are medicals, so they are sort of competing each other. And finally, we realize on OpenAlex and Grobid, which, as any tool, can have some misinformation that could affect our accuracy. But here are some recommendations. First, for dataset provider, we believe it's important to release a paper with the datasets to have something easy to cite and benefits from the citation tracking tools. But also, as we mentioned with the ACDC incident, having a proper and unique name is also important. Now for authors and the community, maybe like an obvious statement, but it's not always done. Documenting the data that we use and following dataset providers is something very important, but most of all, working towards a standard way to acknowledge dataset usage is something very important and would ease the extraction. We could, for example, take inspiration of some venues that ask for a specific data availability section in papers and add it into the guidelines. I want to acknowledge the co-authors and other members of our lab in Copenhagen. And thank you all for your attention. You can find all the links to the paper and also the different tools I presented in this presentation. Thank you all.
Thank you very much. Are there any questions? Comments? Yeah, there's a question.
Hi. Yep. So interesting talk, and I think it's a really relevant topic. I actually had a question with regards to maybe something you could suggest. So what you typically see in a lot of literature is people still use these old data sets because they're the ones that came up with the baseline. So if you want to compare methods, you want to use the same data set, and so these just keep propagating forward, even though they're old and kind of retired. So do you have any recommendations, for instance, how authors or researchers can make a transition to newer data sets and forget old baselines? Because this is something also asked for by reviewers many times, for instance. And the second thing is there a way that data set providers can retire data sets in a way where no one else can use them anymore because they are effectively outdated and should be deprecated completely?
So to answer your first question is what I call in the paper the snowball effect of datasets that are used at first are more known, so more used, and so on, so on. I'm not sure there is some specific recommendation for it, aside from asking people to use more diverse datasets. But it's more like a recommendation than something you can force, because we can't really provide, for example, like a threshold, like, okay, if the dataset is like 5 years old, then you shouldn't stop use it, because sometimes just dataset is hard and you should keep using it. So it's something really difficult to assess. Maybe in some studies, it also shows the lack of real improvement on a dataset that shows sort of a plateau for the results. Maybe this should indicate that we should move on to a new one if it's like high result, of course. And then your second question, I'm not sure I remember.
Yeah, so the second one was, how can dataset providers deprecate their dataset, like, because it's no longer relevant or has some biases that are now spotted?
I think it's it should seem easy to do, but it's difficult in the end, because if you are the only provider, you just have to remove it from your website, for example. But we saw in other study in our lab that, for example, datasets are often re-uploaded on Kaggle, for example, and you sort of lose control on these datasets. So better control should be applied on those data sharing platform, I believe. And so yes, in the end, if it's more control, you just have to remove them from the source, and little by little it will be disappearing, I guess. Thank you for the question.
Thank you. There's a question in the front.
Yeah, thank you. Very interesting. It's more a suggestion than a question. I was wondering, I have noticed that sometimes, quite often, people don't use the entire data set. So for data sets that I know, I find papers that, like, you have 1,000 cases in the data set, and in the paper, out of nowhere, you have 700 patients, you don't know why. Is it something we could systematically analyze using your tools that analyze the papers? Because I think there is something behind, like it's cherry picking or something like that.
No, it's not possible with our tool. I agree, it's a very important question. Also regarding versioning of different datasets, not only like part of it, but for example, BRATS has multiple versions, and we don't make the difference between them. Then yeah, I agree, it's very important, and I mentioned the Kaggle problem before. It's also part of the problem that some people upload different versions of the same dataset with some minor modification, and in this case, we sort of lose track of what is already really used in paper. So it would be like a nice addition. I agree with you. It's very important information also. Yeah. Thank you.
There was a question in the front. Karim, you had a question?
It was the exact same question than the first guy, but I just perhaps to add, because I'm the PI of the M&Ms, and we are kind of frustrated because ACDC was one hospital, and we had to talk to 6 hospitals, and it was really a lot of work, and we think it's a nice data set to test generalizability and so on. But you're totally right. For some reason, people keep using ACDC. If I was a reviewer, independently of the fact that I'm PI of M&Ms and I'm biased, of course, but independently of that, I would suggest to use M&Ms, because you can then test generalizability across vendors and protocol and so on. But people keep using ACDC, they love it. And yeah, it's a kind of interesting phenomenon. Yeah.
Maybe to comment a little bit on this one, another information is that it may be something that we could solve if we have multiple datasets per paper, but in another additional result that I didn't show is that we couldn't find such co-occurrences between datasets. It was very often only one dataset per paper, but yeah, maybe that's something we can also improve, and maybe foundation model could solve that by combining those datasets, I don't know.
Let's thank the speaker.
Okay, moving to the next talk on transfer learning models.
by Ganshan Pudal. So, floor is yours, and please keep it to 30 minutes.
Good afternoon, everyone. I'm Confounder from NAMI, and I'm presenting our work on exploring transfer learning for segmenting medical images. So, typical segmentation model based on encoder-decoder architecture using unimodal data usually looks like this, with some limitations. They are usually constrained to the predefined foreground classes we fixed during the training time, so they require retraining whenever new classes are to be introduced. Similarly, they do not have scope for injection of auxiliary information, so making human interaction minimal, and they are not very explainable. Multimodal image segmentation guided by auxiliary prompts, on the other hand, allow human interaction, and language prompts in particular have potential of some more benefits like this. So let us see an example of using prompts for segmenting these images. These are two different slices of CT scan with liver and inferior vena cava. So example of bounding box prompts and language prompts would be like this, and it can be clearly seen that language prompts in compared to bounding box are more richer and expressive. So what are the recent advancements in leveraging these rich and powerful textual prompts? So nowadays there are vision language foundation models that are trained on large pair of image and text, and vision language segmentation models are built on top by utilizing the knowledge of those foundation models. And these works are mostly done in natural domain, and some of these models have been fine-tuned further in medical data or trained entirely from scratch. So with this context, two key questions arise. How does transfer learning of these models to limited medical data look like from models in natural domain? Similarly, are these models really leveraging the rich semantics that text prompts have? Let's look at some of the recent vision language segmentation models. A typical vision language model would look like this. It has two paths for text and image, and it jointly learns representation for both the modalities. And these models are usually trained on millions of image and text pair. To build a segmentation model by extending these models, we can utilize the powerful representations learned by VLM and add task-specific care for segmentation. So a typical and one of the most popular example of such a vision language foundation model is CLIP. CLIP has been trained on 400 million image text pair with a simple idea. All it does is it uses contrastive loss to bring image text pair that are similar together and dissimilar apart, allowing image encoder and text encoder to be jointly trained. So reusing these encoders that have learned powerful representations for building VLSMs is interesting. One such way to do it would be what ClipSeg does. It simply projects the encodings from both the encoders and feeds it to the segmentation decoder, and then trains this whole model. Another model, Chris, on the other hand, has some extra construct to allow early interaction of the embeddings instead of simply passing them directly to the decoder. And it also has some additional construct to allow more fine-grained interaction between for token and pixel level interaction. So we've talked about vision language segmentation models in natural domain, but what about for medical domain? Well, in medical domain, a version of CLIP called Biomed CLIP that has been trained on 15 million biomedical image text pairs do exist, but there are no VLSMs that have been built on top of Biomed CLIP. So one potential design of a VLSM based on Biomed CLIP would be to extend idea of CLIP-SEG and simply use the same architecture by replacing CLIPS encoders with Biomed CLIPS encoders. In that, one way would be to use CLIP-SEG decoder architecture by randomly initializing it, and the other way would be to utilize pre-trained decoder because it is at least familiar with the task of segmentation. So with these models in hand, we present a benchmarking framework with 4 models I talked about, and we design experiments to answer these key questions. And for that, we utilize 11 different data sets, including radiology and non-radiology, and incorporating different modalities, organs, and pathologies. So how do we generate prompts for our data sets? In a real clinical setting, we would have an expert giving us prompts for our image. That's what we would want to mimic. But since our data sets do not have prompts already existing in them, we resorted to automatically generating prompt from the information already existing in the data sets. One way was to use image processing on the mask to obtain attributes such as number, size, and location. The other was to pass the images to VQA model to get color and shape of the target. And we also used online journals to obtain class-specific description of the targets we wish to segment. So unlike other attributes that change with images, these attributes are a set of 5 or 6 attributes that can be applied to any of the image of that particular class. Similarly, some of the radiology data sets we used also had metadata and radiology reports. So we have extracted a few attributes from there as well. So using all these attributes, we build prompts of growing complexity of up to 9 types for each of the data sets. One example would be for endoscopy data set, P1 looks like this, P2 like this, and incrementally up to P9, it would look like this. Similarly, the final prompt for breast ultrasound data set looks like this. For CAMUS, it looks like this. For checks localize. And for other data sets, it looks similar. So what are the key experiments we performed, and what do the results say? Does making prompt richer from P1 to P9 have any significant improvement in fine-tuning performance? Well, results say not much. So the parts highlighted with red are the performance of the 4 models during fine-tuning. So for each of the data set, on x-axis, prompts are on increasing level of complexity, and the dice score corresponding is on the y-axis. So we see that the performance during fine-tuning on addition of prompts almost saturates after adding initial few attributes. And how do models pre-trained on medical image text pair perform? So compared to CRIS and CLIP-SEG, we can see that Biomed CLIP-SEG and Biomed CLIP-SEG-D, which are familiar with medical domain of green and red color, are always inferior in performance. So we can see that the large-scale pre-training Chris and Clipsig have, and the familiarity with the segmentation tasks they have overpowers the domain knowledge of Biomed Clip. So it does not perform any good. Similarly, another important question we wanted to ask was if the models actually capture language semantics well rather than simply reporting the scores. For that, we designed two kind of perturbations to our prompts during inference. We can look at the bottom of this slide. One was to replace the attributes by rather uncommon English words, and the other was to replace with common and exactly opposite English words. So for each of the data set in the graph here, left represents the experiment on the left side and right represents the result for experiment on the right side. So our hypothesis with these two kind of perturbations was that if the model really cares about language and understands language, it should be more disturbed when the attributes are replaced by semantically opposite words compared to random words. And our results show that Chris is quite in line with that, not for all attributes, but at least for size and location. And this hints that Chris is more influenced by the semantic of text, whereas Clipsig does not seem to be disturbed by this much. So qualitatively visualizing this, we can see that Chris's output changes with change in prompts during fine-tuning, during inference, whereas Clipsig does not care when we replace small by large or top by bottom right. So are these models robust to out-of-distribution data set? So we conducted experiments by comparing them with conventional model, and when conducting cross-dataset evaluation among 5 endoscopy datasets, we found that compared to conventional models, Chris and Clipsig are robust to out-of-distribution data. So these are the key takeaways from our result. And a final message that text prompts are indeed powerful, but more work is needed in building models that can actually leverage power of text prompts, because our experiments show that the models, despite achieving good segmentation performance, actually don't seem to understand or care about language much during fine-tuning compared to what we had expected. On the behalf of my collaborators, thank you to everyone, and do read our paper. Thank you.
Okay, we have time for some questions. Maybe kickstart the questions. So I'm wondering about how whether language really help particularly language help when you have tons of concepts. Not the case in medical image segmentation. Segment a retinal image, you will not see a heart structure there. Access is very limited. Can you comment about this a little bit? Okay. I was just questioning a little bit the use of language for medical image segmentation, because the set of concepts is typically very, very small. When you segment a heart image, for example, there is no brain structure.
Okay, so yeah, compared to natural domain, the concepts in medical images are very limited, but I have two opinions to this. One is when okay, maybe small, but there are a few concepts that can be helpful in guiding segmentation in medical images. So if we use language along with images to inject those concepts, maybe we can achieve more with less number of data, especially when fine-tuning or adapting these kind of models. And second is in medical image segmentation, so segmenting whole image is really tedious, but giving some additional information that could guide the model is not much of a deal, and that would enable a human in the loop, which is very important for clinical applications, I guess. So that was our motivation.
Okay, questions maybe? No? Okay, we have one. I have many.
Yeah. Thank you for the talk. Maybe I missed it, but on the fine-tune or your training of biomed ClipSec, did you froze any aspect of the architecture, or did you just fully fine-tune? Because I would assume that you maybe forget something of the encoder if you like do the full fine-tuning.
Yeah, we fully fine-tuned the architecture because the different parts had not interacted before, so we needed to fully fine-tune them.
How do you avoid forgetting? Like if you, like the encoder part can then, because you adapt to a whole new data set, like forget its previous knowledge. Like, have you tried freezing the encoder part and only fine-tuning the segmentation head?
That can be a path to explore.
Sorry, wait. I didn't understand. Did you ask me something? Or? Sorry.
I actually did not fully understand your question.
No, I was wondering just if we could go beyond CLIP and if we tried models like Llama or things like that actually encode the text, you know, if perhaps it would be useful.
Yeah, that could be, but for now we focused on using models that understand both language and image, but using models that understand language better could help and could be an interesting direction of work.
Okay, thank you.
Okay, let's thank the speaker again. So moving to the next talk. Okay, a talk on medical SAM by Quan and colleague. The floor is yours.
Okay, thank you for the introduction. And I'm Zikang Xu from University of Science and Technology of China. And I'm very happy to be here to introduce our work, SciSam, Medical SAM meets Sign Window. And in this talk, we want to try to solve the problem of medical volume segmentation by utilizing the powerful SAM. And first, as we know, with the development of deep learning, foundation models have shown its power for various downstream tasks. And for example, in 2023, the Meta proposed segment anything model, which is an interactive segmentator trained on large amount of natural RGB data, and it has shown good zero-shot performance on various downstream tasks. And to help those who are unfamiliar with SAM, I want to introduce the pipeline of the segmentation model. That is, for example, it takes an image as the input and encodes it with an image encoder, and also accepts prompts such as points, boxes, or text, and encoded them using a prompt encoder. And finally, we merge the feature of the extracted from the image and the feature extracted from the prompts, and using a mask decoder to predict 3 possible segmentation masks for the given image. So, as the SAM is very powerful, how can we directly adopt SAM for medical images? The answer is yes. Some of the medical data are RGB or grayscale images, such as dermatology, chest X-ray, or retinal OCT. And the answer is also no, because the gap between the natural and the medical is too huge, so that we cannot direct apply SAM on it. There are mainly two gaps between the natural and medical. The first one is the domain gap. That is, for example, as we know in the natural images, the objects are varied in color and shape, while in medical data, the organs usually have a relatively fixed shape, and the color between the organ and the surroundings are actually similar to each other. And the second gap is the dimension gap. As we know, the original SAM can only accept the 2D image as input, while there are some 3D image in medical data, for example, CT or MRI. Actually, we can split the 3D volume into 2D slices and using the original SAM to process them one by one. However, this pipeline requires heavy annotation effort. That is, if we want to segment image with about 200 slices, we need to generate 200 prompts on it. And besides, as the original SAM can only accept 2D images, it cannot fully utilize the information between the slices. So in this paper, we aim to improve the utility of SAM on medical data by mitigating the two gaps. And how to fill the domain gap? Actually, we believe that the fine-tune on medical data is the correct way. So we categorize 15 publicly available datasets, which have images come from head, chest, abdomen, and pelvic. And except for the pre-annotated data, we also use pseudo-annotated data. That is, for the unlabeled medical dataset, we split them into 2D slices using the original SAM to get all labels of the input image, and using a threshold to filter out the labels with low quality and to enlarge the training sets. And how to fill the dimension gap, as shown in this figure, the top line is the 2D SAM and the bottom is the slide SAM, and several modifications are made, especially about the organization of the input image, the architecture of the image encoder, and the mask decoder, obviously. And specifically, as for the input image, as we know, the original SAM can only accept the 3-channel image, that is R, G, and B. And in our medical data, we replace the 3-channel image with 3 adjacent sizes, that is size DI-1 to DI+1. And for the feature encoder, we add LoRa parts on it to learn the medical domain knowledge, and just for fine-tuning, as we know, it's a powerful fine-tune method. And in the mask decoder, the general SAM can only have one convolution transpose layers to predict the mask for the entire image, and also only one MLP layer root to improve to predict the segmentation mask for the image. And here we replace it with 3 convolutional transpose layers and 3 MLPs to generate masks for each size. And the train of our size SAM is supervised by a hybrid loss. As we know, the mask decoder have 3 slice-wise predictions. That is mask 1 to mask 3, and we use weighted loss of cross entropy and dice loss to measure the difference between the predicted mask and the ground truth mask. And as we know, the mask decoder also have another type of output, that is the predicted ROU score. And we use the MSE loss to measure the difference between the predicted loss or predicted ROU score and the ground truth ROU score between the predicted mask and the ground truth mask. And the overall loss is a combination of the 2 loss. And as our size SAM can both accept 2D slices and 3D volumes, maybe 1 slice or 3 slices, so we use an indicator function I to ensure that only the correct part is used for computing the loss. And here comes the inference stage. Actually, in our slice SAM, we only need to select 1 slice from the whole volume, that is slice DI, and we generate prompts on it. Then we use slice SAM to predict 3 masks for the adjacent 3 slices. And then we slide to slice di-1 and use the information predict mask as the prompt for the next round of prediction. That is, we get the bounding box of the predicted mask of slice di-1 as the prompt, as a box prompt, and then we can get the prediction of slice di-2, slice di-1, and slice di. And following this propagation procedure, we can generate the mask for the whole volume. Just as the figure shows, we can broadcast to the whole volume, and therefore the prediction of the whole volume is generated like the figure shows. Besides, in order to improve our model's utility, we also conduct post-processing methods. That is, as we know, the SciSam can have 3 predictions of the given image, just as the original SAM does. And we remove the masks with an IOU lower than 0.4 and and masks with a stability lower than 0.6. And finally, we use erosion and dilation operations for the predicted mask to get the final predictions of the given image. And here comes the result part. In this slide, we only use bar plot for visualization. And if you want to get the detailed number, you can turn to our paper. And as a result of the BTCV dataset, when we use points as prompt, we can have a better performance compared to other SAM variants. And if we use boxes as prompts, we can have comparable performance compared to other variants, while our SliceSam requires fewer prompts. And the BTCV dataset is an organ segmentation dataset, and we also conduct experiments on tumor segmentation datasets, and we find that our SliceSam can outperform supervised methods, including NUNet, Informer, and 3Unator, and SAM variants, including SAM-B and SAM-3D adapter, significantly. We also, similar results are found on the Word dataset. It's another commonly used dataset, and we find that our SliceSam can still outperform other methods. Besides, we replace the backbone of our SliceSam, which is VIT-based, with VIT huge, and we find that it can further improve the performance, especially on the 4 perhaps more difficult tasks, including the adrenal, the pancreas, the intestine, and the colon. And we also visualize the output of SAM variants and our SliceSam, and we can find that compared to the other SAM variants usually have inconsistency between the sizes and maybe have some missing parts, while our SliceSam can have more smooth output, which is better for the clinicians to diagnose. Then we evaluate the noisy prompt robustness of our SliceSam. That is, we modify the box prompt by translation or scaling, and find that although we add noise to the box prompt, it can still have it can still have a precise predictions. And then we evaluate the generalizability on heterogeneous datasets, which varies in modality, the spacing, and the body part compared to the training set. And this is an in-house dataset, and we find that the fine-tuned version of our SliceSam can outperform fully supervised models for about 15% on this in-house dataset. And we think that this is because our SliceSam can adopt the prior knowledge from the large amount of medical data and the natural data, while the 2 fully supervised methods are trained from scratch. And in conclusion, we propose SliceSam, which is a 3D variant of the segmented entity model. We bridge the gaps between the natural and the medical, and bridge the gaps between 2D and 3D. And extensive results on medical datasets show the effectiveness of our SliceSam for all of these medical datasets. And we believe that SliceSam can benefit the whole society, reduce the annotation burden, and ensure health equity for the marginal populations. And last but not least, the co-author of this paper, Zikang Xu, is seeking for talk positions in for 2025. And if you're interested in me, feel free to contact me, and I'm happy to take any questions. Thank you.
Okay, we have time for a few questions. Okay, we have many requests. Let's start there.
Really nice work, and you claim that you fill in the gap for the nature images and the medical images. So I just wondering, because you introduced some way to fine-tune the SAM like LoRa, etc. So have you ever tested back after you fine-tune the SAM? Have you ever tested back to the originals, like original nature images? I mean, after fine-tuning the SAM, do you think the performance is going to decrease when you doing the nature image segmentation task?
Well, thank you for your question. Actually, we did not use the fine-tuned version of SAM on medical dataset into the original, maybe SAM SA 1 billion dataset, and we think that perhaps the performance on the natural images will not increase, as we only train we only fine-tune the SAM, our SAM on the medical data, and perhaps it's more like a maybe expert model rather than the foundation model. This is our SAM is focused on the medical domain. Yeah. Okay, thank you.
Thank you for your presentation. I have a question regarding ambiguity resolution. So for instance, in case of SAM, if you specify 1 point or a bounding box, they predict minimum of 3 segmentation masks. Could you please tell us how you do it in your case?
Well, in our paper, we resize the medical image into 1024 by 1024, and we actually this resolution perhaps is not very good enough for precise precise medical diagnosis. And I think this is mainly because the problem is how to use the high resolution part of the SAM model. And actually, in our paper, we do not focus on this direction, but mainly focus on how to use 2D SAM for 3D segmentation. Yeah.
One more question.
Okay.
Do you support text prompts?
No, we do not. We only use points and boxes and as prompts. Yeah. Because actually the open source version of the original SAM, it also only uses points and boxes. Yeah.
Thank you.
Thank you.
Maybe one last question. I was asking that. At the bottom.
Okay. Hello.
Hello.
Thank you very much. I would be especially interested into your intuition behind some of the losses, especially the IOU loss. Why you came up with that, of using that? Has it any added benefits?
Sorry, I didn't get your question.
You have the IOU loss where you predict the IOU score.
Yeah, actually, the original SAM, the original natural SAM have 2 type of outputs. That is the masks and the IOU score, and we directly use the same as the original SAM, and to compute the IOU score between our predicted mask and the ground truth mask. I think this is the type of method that try to something like calibration. That is, the SAM model can directly predict the IOU score without knowing the actual segmentation ground truth. Yeah.
Okay, maybe last question, very last question.
Thank you for the presentation. So I was wondering, what are your intuitions with regards to applying your method on medical imaging, which does not particularly include healthy patients? For instance, if there are tumors or lesions or anything that may not represent the true healthy patient distribution. This is my first question. And my second one is that if you think that the method, if you think SAM or MedSAM could ever reach a point where it does not need any kind of prompts like bounding boxes or any of the sort of user intervention to do the synchronous stage, because we don't always have bounding boxes and things.
Do you mean the first question is why we mainly examine our results on organs rather than tumors?
My question is more when you, even if you want to segment organs necessarily, if you have an image with a tumor, the organ itself and its anatomical characteristics change a little bit. That's why like registration or using templates, including, for instance, healthy tissue, that is trained on healthy organs and healthy images, doesn't necessarily always work. So I was wondering your intake on this one, on this part.
You mean the difference between the healthy objects and the illness objects? Sorry, I didn't get your question.
Basically, your intuition on the prediction if the images are not healthy.
Most of our data sets are illness subjects, and we have to use it because we collect the public available data sets, and most of them are have some illness in it, and so we do not have special processing between using healthy subjects to train our model or the illness subjects.
So there is no distinguishing between healthy and unhealthy?
Yeah.
Thanks.
Thank you.
Okay, let's stop it here, and this will conclude the session. Okay, thank you.
Okay, before you leave for the break, please do keep in mind to take down your poster at the end of this poster session. Do not wait for the end of the day. Please do it at the end of the poster session.
Or I'll just
Okay, yeah. Okay, hello everyone. Welcome back to this last oral session of the conference. So this is a Melba Journal to Conference track. And so I will let Tal and Hugues present maybe this session. Tal, I don't know if you wanted to say a few words about Melba, but please go.
Okay, so I'm Hugues Talbot. I'm a professor at Centrale Supélec, Paris-Saclay. And I'll be very happy to co-chair this session.
Hello, everyone. I'm Tal Arbel from McGill University in Mila and editor-in-chief of Melba. So just to let you know, Melba is a free archive overlaid journal, relatively young, working in the intersection of machine learning and biomedical image analysis. And we have been experimenting with the journal to conference track, where we invite all accepted Melba papers from the year to present their work at a conference, only those papers that have not been presented at other workshops or conferences. So we're very grateful to MIDL for allowing us to have a wonderful collaboration on this exciting journey and allowing us to have Melba papers present today. So we have 3 orals today. We actually have 4 Melba papers, 1 that joined late, and they all have posters. So without further ado, let's get started with our first paper.
Aisha will be presenting her work on, it's all gone, hyperpredict, estimating hyperparameter effects on instance-specific regularization, and for deformable image registration. So, and Aisha is from the University of Sussex.
Hi, everyone. I'm Aisha Lowell, and the title of my talk today is Hyperpredict, Estimating Hyperparameter Effects for Instance-Specific Regularization in Deformable Image Registration. So supervised by Eva Simpson. We're both from the University of Sussex and both members of the Sussex AI Research Group. So before I go into what it is that we are proposing, I'm going to just give, for the benefit of everyone, I'll give a brief overview of what image registration is, including the objective function. So basically, image registration in simple terms is an alignment problem. So technically, what this means is that given 2 images, the first is a moving image and the second is a fixed image. What we're trying to find essentially is this optimal transformation T that transfers the moving image to the coordinate space of that of the fixed image. So now let's look at the objective function. But before I move into this, right, I just want to highlight that what we're proposing is not a new registration method. Rather, we are proposing a method that makes the process of image registration more effective, right? So typically in a registration method, we have 2 competing objectives. The first is a similarity term that tries to ensure that both images match. So how this works is that you have your image pairs, you pass it through your registration network. You derive this deformation field that tells you at each location where you should move the moving image to get to the coordinate space of that of the fixed image. And then you compute the spatial transformation based on that to derive the moved image, right? So your first objective is trying to minimize maximize the similarity basically between your moved image and the fixed image. But then the problem is that we cannot optimize for this term alone because we have a large set of possible solutions. So we need to somehow constrain this. And to be able to do that, we introduce some form of regularization. And what this tells us is that we have a large set of possible solutions, but we're only interested in those that are plausible. So how do we know how well our image has been registered? We can look at two metrics. The first of them is the DICE score, which I think almost everyone is familiar with. But in registration, basically, you have what was defined here as your deformation field. You acquire moved labels, that's the segmented, moving, and fixed image. You transform that based on this spatial transformation, and then you derive your moved label. So you compute your DICE score between this fixed label and the moved label, right? So obviously regions where you have, if you have a higher, we sort of want to have higher DICE scores, that's DICE scores closer to 1. And another method of evaluation is by looking at how smooth our deformation field is. So if you look at the Jacobian determinants, where regions that you have values greater than 1, it means you have local expansion. And if you have less than 1, it means you have local contraction. And then if you have like a negative value of the Jacobian determinants, it means you have some folding within that region. So typically we try to avoid or limit the number of negative values of the Jacobian determinant that we have. So if we try to sort of look at the effects of regularization, which is basically lambda here that you see in this equation, you can see that with visually it's a bit difficult to sort of notice the difference between, so these are registered images, right? The first one is when we have no regularization at all. And the second one is when we have some form of regularization, that's the value of lambda here is greater than 0. So visually it's a bit difficult to see whether that it's basically they look like similar images or the same images. So that's why it's important for us to sort of examine what the deformation field look like. So with no regularization at all, we can see that we have more folding within the deformation field. And then if you have some form of regularization, you can see that you have a smoother deformation field, right? And it turns out that the optimal value of lambda varies per subject, and it also varies per anatomical region. So what you're seeing in both plots here are DICE scores plotted against different values of lambda. In the first one, you see 5 different points. So these are 5 different subjects, and we have 5 different optimal values of lambda for so we have yeah, so we have 5 different optimal values of lambda for the different subjects. And the second one here, basically, is saying that we have different anatomical structures, right? So we have different optimal values of lambda for different anatomical structures. So basically, in essence, what this means is that if you're trying to optimize for the hippocampus, for instance, you have a different optimal value of lambda compared to when you're trying to optimize for the putamen or the ventricle. So these images were adopted from the hypomorph paper, if you're familiar with it. So given that we've seen in the previous slide that this optimal value of lambda varies per instance, how do we then select what the optimal value of lambda should be for specific cases? Traditional methods of sort of selecting these optimal values by doing cross-validation. So that's when we discretely sample values of lambda and we pass them through your method, your model, and you derive a result, right? And you then select the optimal value of lambda that, for instance, gives you the highest DICE score, and you use that single value across the entire test data set. But then we get suboptimal results, right? Because as we've seen in the previous slide, this optimal value varies depending on instances, right? And also, if we're trying to define a specific criteria, we have to do that at cross-validation time. And we cannot select this value based on instances. So what we're proposing here in HyperPredict is that given that we've seen that we can sort of measure the effects of registration, so we can sort of measure how well our image has been registered by looking at these 2 metrics, which is the DICE score and the number of folder voxels. Can we sort of establish a relationship between an image pair, there's a moving and fixed image, a continuous range of hyperparameter values, and the resulting metric? So what we do here is we train an MLP that takes as input an encoded representation of your image pair, as well as a continuous range of hyperparameter values, and in turn, it outputs 2 heads. The first one is the DICE score of 35 different structures of the brain, and the second one is the number of folder voxels. In order to train this, we obtain training data from 2 different registration methods. The first one is SLIPE-RNN, which is a deep learning method, and the second one is NIFTY-REG, which is an algorithmic method. So what this means basically is that at test time, we don't need to run our registration method multiple times in search for an optimal hyperparameter. What we can do basically is we can select which I'm passing our image pair a continuous range of hyperparameter values and derive the predicted metrics. We then select the optimal value based on what was derived. We pass that single value through a registration method, and we obtain our deformation field. And an added advantage of using hyperpredict is that we have this flexible selection criteria at test time. So basically what this means is that we can say that we're only interested in some values of lambda. So in our case, we're saying that we're only interested in values of lambda that lead us to having number of folded voxels less than 0.5%. So we have this criteria we can tweak based on our preference at test time. So moving on to the results, first of all, we analyze the predictive ability of hyperpredict, which is basically how well are we able to predict the target metrics. So in both plots, these are Blunt-Altman plots, and these are the differences. On the y-axis, you have the differences between the predicted and target metrics plotted against the mean. And ideally, we would want this to be within the boundaries of the line here, which we see in both of them. And also, if we compare hyperpredict with cross-validation, although we notice that we have comparable dice scores with the pallidum and amygdala, we have hyperpredict tends to, so hyperpredict is the green one here, and cross-validation is the yellow one here, yeah. So if we look at the amygdala, hyperpredict performs a little bit better than cross-validation for the dice coefficient. And if we look at the number of folded voxels, we see that we tend to derive more plausible deformations, right? Because we would want number of folded voxels to be less. Ideally, that's what we want. So we can see that if you use hyperpredict, we have less folding in deformation field compared to when you use cross-validation. So this is also comparing hyperpredict with cross-validation, but this is more pairwise. So in the first plot here, what you're seeing is for that of the dice score. So on the y-axis, you have hyperpredict of the dice score for a particular pair, plotted against cross-validation for the dice score of the cross-validation for that particular pair, right? So because we prefer dice scores that are high, we would want more of our points basically to be above this line, but we see comparable dice scores, right? But then what's interesting is that if we do this pairwise comparison for the number of folded voxels, we have just less than, I think we have less than 10 values here. So for number of folded voxels, we want it to be lower. So we prefer solutions that are basically here. We have less than 10 points where cross-validation does better than pairs, where cross-validation does better than hyperpredict. And since we're proposing something that is instance-specific, we are looking at the distribution of the optimal hyperparameters. So the first one is the distribution of the optimal hyperparameter for different structures. You can see that it does vary, so it's really important to select the optimal value based on specific instances, and this is across subjects as well. So we can't, it's not optimal to use a single value across the entire test set. So given that we've derived these predicted values from hyperpredict, it means that for thalamus, we've seen that based on this plot here, I don't know if it's clear, but based on this plot here, you can see that the optimal value of thalamus is 0.09. We can pass that optimal value at test time to our registration algorithm, in this case, syllab iron. So all the results I'm showing now is just for syllab iron and not nifty-reg. We pass that to our registration algorithm, and then we derive the registered image, optimizing for the thalamus. And then same for the amygdala, we can see that what hyperpredict proposes is using an optimal value of 0.16 to optimize for the amygdala, and we pass that through the registration algorithm, and we optimize for the amygdala. Finally, if we look at the computational efficiency, we can see that because we are not running our registration method multiple times in search for an optimal hyperparameter, we can sort of test thousands of hyperparameters within a short period of time. So with hyperpredict, we can test around 0.84, we can test around 8,000 hyperparameters in just 0.84 seconds. So in conclusion, we've shown that we can sort of establish a relationship between our image pairs, lambda, and a continuous range of hyperparameter values, lambda, with the registration metrics. We've also shown that this lambda value does vary per instance. And we have this flexible, tweakable selection criteria at test time, and we don't need labeled data. We have CSV files for those that are interested that contain the lambda value, that contain registered image, the solutions of registered image pairs, basically. So if you're interested, please head to our GitHub. So in future, we're looking at different organs or registration methods, because our method is agnostic to data sets and regularization, basically. And then we'll look at exploring other registration metrics, such as the Hausdorff distance, and training different image encoders to see if there's a difference between, or if we have improved results. So these are my references. And thanks to my colleagues at the lab, feel free to scan the code for either the code or the paper.
Thank you for a great talk. We are on a tight schedule because we have to vacate the premises at 6, and we also have the awards ceremony just after this, after the 3 talks. So we have time for 2 questions. So who would like to ask a question?
Thank you for the presentation. I was wondering if I maybe missed it, or so you have a different optimal lambda for different organ on the same image, right?
So we have different optimal lambda for different structures or different pairs, different subjects, yeah.
Mm-hmm. So if you wanted to register, so there's no optimal registration of 2 images together that would optimize, that would have the optimal lambda for all the structures.
So optimal lambda for all the structure does not exist, right? Because we have different optimal values for different lambda.
Yes.
Yeah, exactly.
Yeah. But so is there an optimal registration process that maybe not a single number, but like a lambda field, or I don't know how to call it, that you would, based on your research, be able, or based on like future work, optimally register 2 images to one another, based on all structures that you know of?
But then the structures do vary per lambda, right? So unless if you don't care about optimizing for each structure independently, you could use one hyperparameter for the entire distance, but it does not optimize for specific structures. Do you get what I mean?
I think so, yeah. Thank you.
More question?
Yes, thank you. The question would be, how do you initialize the lambdas, and did you try to mess with it and like putting in negative numbers?
How do we, sorry?
So how do you initialize the lambdas to optimize the right lambda?
Okay, sorry.
And then did you try to mess with that in like form of like putting negative numbers?
So if I get you right, how do we maximize the lambda?
Yeah, no, how do you find the
initialize
optimal lambda, and did you try to mess with that?
Okay, so what we're using at train time is a continuous range of lambda values, right? So we have, we sort of normalize our values between 0 and 1. So I don't know if that answers your question, or if that's what you're asking.
No, but I can ask you later. That's fine.
Okay, how do you initialize? Okay.
Thank you very much for these questions, and please join us to thank the speaker.
Okay, our next talk is leveraging SO3, steerable convolutions for pose-robust semantic segmentation in 3D medical data. And our speaker is Ivan Diaz.
Thank you. So, how do I make this big? Okay, how do I make this big? Full screen. Okay, I guess just like that. So thank you for the introduction. This work is done between myself and Richard McKinley. We work at the Inselspital in Bern, and Mario Geiger, who works for NVIDIA. So we'll first talk about the concept of equivariance. Equivariance, many of you are familiar with it, but for those of you that are not, yeah, thank you. It's basically, here's an example. You have an input. You apply some sort of an action, like a rotation in this example. You have a layer, like a segmentation network, and you get an output. Now this should be exactly the same as taking an input, putting it through the layer, and then applying the rotation. This output should be the same. So this is the classical graph that is shown whenever we talk about segmentation. If you have an X, some input X, you apply a function Y, a function F, and you get a Y. Then you do a group action on Y. Should be the same as doing X, applying the group action on X, and then the function. You should have the same result at the end. So more concretely, what does this mean? If you take an input like a brain MRI, and you segment it, and then you take that segmentation and you shift it over a certain number of pixels, you should get the same result as if you shift it over a few number of pixels and then segment it. This is equivariance. So regular convolutional CNNs are translation equivariant. That means that it doesn't matter if you segment first or segment after doing a translation, you get the same result. What about rotation equivariance? In this case, regular units are not rotational equivariant. So if you take an input, you rotate it, you segment it, and you take the same input and segment it first and then rotate it, you get a different answer, which is, it's not optimal. So what is usually done if we care about having something that is equivalent to rotations is we feed in rotational data augmentation. So you just send into the UNet rotated versions of the image. So this is okay. This seems to work. But here I work in the neuroradiology department. We care about brains, and we have very big volumes, and we're working in 3D. And in 3D, if you want to teach a network through rotational data augmentation, full rotational equivariance, it estimated that it takes about 500 different rotations to learn. So one thing that we can do is just make a network that is rotationally equivariant out of the box. And what this is based on is on a package called E3NN, which implements equivariant neural networks. And the heart of my network is an equivariant convolution. And this very big formula is basically explaining that you are using a basis of spherical harmonics, which are on the right, some sort of radial basis, which is arbitrary, and these learned parameters. So it's a little hard to explain in just a few minutes, but you can think of this convolution as a kernel that's in space, and that you can that is learning the radial information from the data, and that you can resample and apply as a normal kernel in a regular unit. So the network architecture is just a unit. You guys are familiar with the original unit. So we have a 3D unit. We have a kernel diameter of 5 pixels. And for the experiments that I ran, I did 5 by 5 by 5 kernel size. There are some technicalities when you make a network that should be equivariant. You should have some sort of equivariant pooling and equivariant upsampling and equivariant nonlinearities. These are all explained in the paper. But as an example, if you have some sort of data that is like a vector, and you just pick the maximum value as you would a scalar of the 3 components of a vector, you don't get the right answer. You should instead pick the maximum norm of the whole vector. Now I will talk about the heart of the way that this data is represented, which are called irreducible representations. So these are basically indivisible representations of groups, and the groups that we're talking about today are SO3. They are basically, they explain how data transforms. And you're familiar with scalars, which transform as scalars, vectors, which have a direction and a magnitude, and then you have higher order, the rank 2 tensors, and higher and higher. So instead of using a top layer of 30 input scalar convolutions like we do in regular units, we had to pick some sort of equivalent combination of input irreducible representations. And we did some experiments on segmenting a brain structure with 8 scalar irreps, 4 vector, and 2 rank 2 tensors. And these are all the different ratios that we use. So for example, this second column, it shows only 30 scalar irreducible representation. This one has no rank 2 tensors, and this one has equal amounts of scalar, vector, and rank 2 tensors. And the one that best seems to work is the one that has more vectors, more scalars, half vectors, and a little of rank 2 tensors. So now that we have that, we ran some experiments. The experiments were very simple. We just trained our approximately equivariant network. We ran a regular 3D unit and the same 3D unit with rotational data augmentation. The data sets that we used were the Bratz data sets for tumor, and the MindBoggle the data set, and we picked a few healthy brain structures. So this is the results for the Bratz data set. Our model was outperforming the other two. That's all I have to say about this one. And this is the MindBoggle dataset. So like I said, we picked 7 different structures in the brain. And then we ran some rotation experiments. So first of all, what is interesting to verify, even though we already knew this, is that the network, our network is quite efficient with respect to training samples. So as you can see, you need quite fewer training samples compared to the other ones to get the same performance at the end. There's also an interesting experiment that we ran showing the performance versus the number of parameters. So here on the left are our equivariant network, which has much fewer parameters than the non-equivariant version. And I also ran the experiments with 2 sets of kernels just to see how it would do. So the version with a higher kernel size, with 5 by 5 by 5 kernel size, did better than the one 3 by 3 by 3. And in the regular unit as well. What's interesting as a take-home message for you, if you remember just a couple things from my talk, is that the number of parameters is the same for our network, no matter the size of the kernel, because we're simply discretizing as opposed to the regular unit, which as you increase the size of the kernel, the number of parameters grows. So yeah, it's independent of the kernel size. And then we ran some rotation experiments, the same 7 structures. What I did was you have an input image, we segmented it, and then we rotated the image and segmented and calculated the dice score. And this is the results as we rotated from 0 to 180 degrees. So our network here, the little one in blue, is always on the top, and you would expect that it would be flat line because it's supposedly equivariant, but there are some voxelization effects. The yellow one is the unit trained with data augmentation, and then we have the unit that is not trained with any data augmentation. So you see the red one as soon as you start rotating the input image, the dice score goes down fast. And then just for our interest, we trained another unit with rotational data augmentation, but only up to 20 degrees. And yeah, so these are the results. So the unit that is trained with data augmentation, full data augmentation, does quite well, but it takes a little bit longer and it performs slightly worse. Finally, we did a comparison with the group CNN. So these are approximations that to the SO3 group, and yes, sorry. So these this network is basically stores rotated versions of a kernel in an extra channel, and I basically ran this experiment on a group which is only equivalent to 180-degree rotation. So it's not really a fully fair comparison, but the memory size was the same. And we see that it performs slightly actually worse than all the networks. So that's the comparison. And in conclusion, I guess the take-home message is that we have a equivariant network to all 3D rotations, so you can just download it and give it a try. It's quite data efficient and it performs well even when rotational equivariance is not necessary. And another thing that I haven't explained is that it takes in any type of input, so you can put in scalars, you can put in vectors, rank through tensors, and outputs as well. All these different types of data that transform differently. So yeah, that's my conclusion. I'd like to thank you for your attention, and yeah, please visit the repository and try it out. Thank you.
Okay, we have time for 1 or 2 questions.
Hi, thank you for an interesting talk. I'm wondering in terms of like real world wall clock time efficiency, like this kernel, I did not quite get, like, could you use like the normal, whatever, CUDA implementation of a convolutional kernel with this, just reparameterized, or would you need like some custom implementation so that it would work well in terms of like doing it fast on a GPU?
Yes, so this one, at the moment, it's a little bit slower than a normal non-equivariant unit, but there are optimizations that are in the pipeline.
All right, thank you.
Yes.
Question? Okay, yeah, go ahead.
Hi, thank you for the talk. So if I understand correctly, your baseline is to add full rotations and as data augmentation, but it's not really capturing the equivariance itself, right? It makes it robust to any kind of rotation, but it doesn't force the results to be consistent. Have you tried as another baseline to, for instance, add a loss term that would, so you would take your batch, pass it through the network, rotate it, and actually make a loss that would make the two predictions match, which is the property you're targeting to enforce?
Yes, the training that I did was just very naive, like you said. This is something that we can definitely try.
Okay, thanks.
Thank you.
Okay, so let's thank our speaker.
And so now we have the last last presentation of the session, score-based generative models for PET image reconstruction by Imraj Singh.
Yeah, thank you. So yeah, thank you for the introduction. So I'll be talking through our work on score-based generative models for PET image reconstruction. And I'm from UCL, I'm a final year PhD student. So first I'll go through some basics of PET reconstruction and then go through some score-based diffusion or score-based generative models, and then talk about a couple of our contributions. So very quickly, so the measurement process in PET is quite complicated. So what happens is we have a tracer distribution, and what we collect are lines of responses going through the patient and being detected afterwards. And the challenges with this is that we don't have too many LORs, or these lines of responses, so we have high noise. And because our tracer distribution can't be negative, our images are non-negative. And the reconstruction process is quite slow because our forward operator, which I'll talk about in a second, is quite large. So framing this in terms of an inverse problem, we can say that our mean of our measurements is, or measurements are sampled from some Poisson distribution. And we can also say that the forward model looks like system matrix A and some backgrounds, including scatter and randoms B. And so an established approach for, to reconstruction is the map estimate. So this is the map objective here, where the likelihood is a Poisson likelihood, and a prior is typically handcrafted, something like a relative difference prior or total variation or something like that. So in literature, these things are kind of addressed. This low photon count, this high noise is Poisson likelihood we use. And then we also have inherent non-negativity to account for the non-negative images. And then for the slow reconstruction process, we can subset our forward operator. So we can go through subsets of our measurements when we're updating our likelihood. And this makes things, makes convergence a lot quicker. So that's a little bit about PET. And then when you also consider it from a conditional sampling point of view, so more Bayesian, you can say that your measurements are some random sampled from some Poisson distribution, and your image is sampled from some prior distribution. And then from Bayes' theorem, we can say our posterior is our likelihood times our prior, or proportional to that, and then the gradient of the log of the posterior is equal to the gradient of the log of the likelihood plus the gradient of the log of the prior. And the idea in this work is to use our score-based generative model to try and estimate this prior distribution and use this to regularize or make our inverse problem more well-posed. So a very brief primer on score-based diffusion models. So we've all heard about DDPM during this conference. So score-based diffusion kind of generalizes that to have a continuous number of time points. Specifically, this drift term and this diffusion term are very, you can tune them to be exactly the same as DDPIM. And the forward process in diffusion or score-based diffusion goes from your image manifold, for example, all your PET images, and it goes towards a Gaussian. That would be a very bad generative model. You'd just be getting noise out. So we want to try and reverse this. So we have we know there exists some reverse diffusion process, which looks like this, which is another stochastic differential equation. And the idea is that we want to train a score model to estimate this, which is our score, which is the gradient of the log density. And we do this using denoising score matching. And thinking about this in a slightly different way. So we can consider our score model as taking a noisy image and treating it as like a one-step denoiser, and you can keep denoising, adding noise, denoising, adding noise to sample from our distribution. And the idea now, instead of just having an unconditional score model where we'd be able to just synthesize PET images, we now want to change that to use a time-dependent posterior, so we want to condition on our measurements now. And we can decompose this posterior into the score model, and neglecting the marginal, but and also the time-dependent likelihood. And this idea of a time-dependent likelihood is a bit difficult to deal with because we only have a likelihood at t equals 0, so when we're not noisy. So we have to approximate this. And there's two methods in literature which deal with this. So the first, annealed likelihood, simply just takes your Poisson negative log likelihood in this case, the gradient of your Poisson log likelihoods are in this case, and applies it on xt, so one of these noisy images. Obviously, because we have non-negative images, our xt could have negative values, so we have to deal with that in our reconstruction. And additional thing is this lambda t parameter. We increase lambda t as we get closer to t equals 0 because we want more likelihood when we're closer to non-noisy images. And DPS is another method. So instead of using xt, we use a denoised estimate instead. And we also have to backpropagate. Yeah, I'll skip to the next bit. And there's another method we can use. So instead of just substituting an approximate for a time-dependent likelihood, we can use DDIM. So instead of sampling or reverse diffusion process, we can say we can denoise and then we can add noise back in this very specific way. And then whilst we're denoising, we also want to ensure consistency with our measurements at this stage, and then add back noise back in afterwards. So this has sort of been proposed in literature. So our contributions in this paper were to suggest a few sampling rules, but also accelerate to fully 3D reconstruction. And we had a couple more contributions which are outside the scope of this talk. So first off, let's just consider having a Poisson, having a Gaussian approximation for a likelihood. This is misspecified because we know there's Poisson noise on our measurements. And you can see, given a simulated lesion in the brain, you can see that when you decrease the regularization, so increase the amount of likelihood, it just completely gets rid of the lesion, which is a very bad thing to see and very dangerous. So we really need this Poisson log likelihood. So now briefly mentioning our algorithm which we propose, the main algorithm we propose is PET-DDS, which uses this idea of accelerating our sampling. And so instead of using 1,000 time steps like annealed likelihood or PET-DPS, we only use 50. And the idea here is that we can, when we're denoising, going from each step to denoising at each step, this can be decomposed into, we're getting a Tweedy estimate, which is denoising with a score model. So we get our clean image back, and then we ensure that image is consistent with our data then. And then we also put that back onto the noisy manifold. And we do this iteratively. So we can sample measurements, which are sample images, which are consistent with our measurements, but also consistent what we've trained our score model to approximate. So our experimental setup, this is all in silico, and we train on images without lesions and test on images with, and we also test with 2 different noise levels. And we have PSNR, SSIM, and then also we look at the lesion detectability, this contrast recovery coefficient, which is very specific to PET reconstruction, and we look at all those for evaluating our methods. So continuing the experimental setup, so we have UNet type architecture from OpenAI with the time embedding and also some attention in there as well. And in 2D, we compare against unrolled iterative methods and also post-processing methods. And in 3D, we compare against an unsupervised deep image prior method, then also some more traditional established method, which is this block sequential regularized expectation maximization with a prior, which is this relative difference prior. And just to recap, so the 3 methods we were kind of considering were on an annealed likelihood, where we're updating based on our XT, this noisy image, this DPS, where we're updating based on some Tweedy estimate, and this PET-DDS, where we're updating, where we have some projection type operation when we're on a non-noisy manifold. And looking at some results, so in 2D, we can see that the PET-DPS and PET-DDS work very similarly in terms of PSNR and SSIM. In fact, PET-DPS is slightly better, but in terms of those metrics. But in terms of your contrast recovery coefficient, something which could be clinically more relevant, the PET-DDS method improves a lot. So this is just a different way of including your likelihood can improve, for example, your contrast recovery or for your lesion. And looking more quantitatively, we can see that compared to, so our supervised methods in this case are trained on data from different noise levels than these, because in this case the labels for the supervised method are the actual measurements from the PET scanner in that case, so the raw sinogram data. So they don't perform quite as well because it's out of distribution, but this begins to, the score-based generative models perform well because all we're doing is injecting some likelihood during our sampling. And you can also see that the timing is a lot, there's a big variation in the timing. So for annealed likelihood, it takes 45 seconds. And for PET DPS, which I wasn't able to go over, but we have to do some back propagation through the network, which increases the time it takes for sampling to 60 seconds. And for PET DDS, it gets down to 4 seconds. And this is all in 2D. And it's worth noting that the CRC is a lot better for PET DDS. And then scaling this to 3D, so we took that PET DDS algorithm, and then the score model we only apply it in 2D. So we need to somehow apply this model in then 3D, so slice by slice. But then we have additional regularization, ensuring coherence in that Z direction, that orthogonal direction to those slices. And we do a similar sampling method. So instead of just regularizing or just projecting based on our likelihood, we add some additional regularization. We also subset other forward operator as well, so we can speed up reconstruction times, having minimal impact on the quality metrics. So we can get reconstructions in fully 3D in about 2.8 minutes. And looking at some of the reconstructions, you can see it's more classical methods can blur out your lesion, whereas PET DDS with some relative difference prior keeps coherency in your axial direction. So where this fails and creates those bright spots, this is more consistent in that direction, and your lesions are sharper. And for our conclusions, we like this idea of separating your image modeling from your forward modeling, and then we're interested in whether we're sampling from the correct posterior and how to better scale the 3D data. And thank you to my collaborators and the funders, and thank you for listening. And if you want to see the paper and everything else, this is a very large QR code, but everything is there. Thank you.
Thank you very much for this nice talk. Do we have time for 1 or 2 questions?
Thank you for the talk. I was wondering, how do you deal with the large matrix, the forward matrix?
The forward operator.
Yeah.
So this is all, we use a reconstruction engine called STIR in the background, which can deal with, so we've simulated like a Siemens barograph, or is it Siemens? MMR, and that was all done implicitly. So it's all matrix free. So we don't have to store a big matrix or anything, and it's done within the software. Yeah. So it can work. This is all in silico, but we should be able to get this to work on real data, but that's for the future. Yeah. Did that answer the question? Sorry. So, okay. Yeah, sorry. Yeah.
More question, maybe? I have one. Your simulated data looks a bit...
yeah.
And also often in PET, even with head data, often there's a lot of motion artifacts. Also blur the data. So is your reconstruction a bit... isn't your construction a bit...
Yeah, like so ideally we would have some really high quality PET images which we could train our score model on. But I guess this is more of a feasibility sort of thing. Like, yeah, ideally we'd have high quality reconstruction, like reconstructed PET data where we'd learn that image manifold rather than this synthetic manifold. Yeah.
One last question, maybe, if I have the time. The log likelihood of the Poisson distribution is not, it has an infinite gradient, so I don't know if it causes problem in your... Often people who reconstruct these data with the Poisson noise, they regularize the Poisson distribution in the sense that they gradient at some point when they optimize.
Yeah, is that like preconditioning? So I think, yeah, in there as well. So during this is a very like this objective function, we actually do a BSREM type update. So that should account for those things. So I think we use a EM preconditioner in there somewhere. Yeah. Yeah.
Thank you. I think we can thank the speaker.
Okay. I'm not sure I would appreciate that. Yes, just. Okay. You were seeing my point. Okay, who starts? Okay. Ouais, restez là. Restez là. Okay, so before we move on to the awards that everyone is waiting for, and the next MIDL's location, of course, just a few words and thank yous, of course. So I think everyone agrees that we had an intense program and a lot of great scientific discussions, whether at the poster or here in the auditorium. We also had 3 great keynotes, Gaël, Laure, and Karim. And there was also some gathering outside of this place, as you may know, and I want to say a special thank you to Mathieu and his team who organized this treasure hunt for the PhD student of the doctoral symposium, and of course the fabulous gala dinner of yesterday. So in addition to the main organization team, we had the company Carte Blanche who helped us tremendously to organize this conference, so we want to acknowledge them here. So if you plan to organize a conference in France, don't hesitate. We didn't get a discount to say that. Okay, so thank you also to our volunteers. We also couldn't have done it without all these red t-shirt people. Okay, thank you also to our advisors, scientific, clinical, and industry. Our sponsors, as we have said in the beginning, Centrale Supélec, and all of our sponsors who not only gave money but also communicated on their works and way of doing. Also a big thank you to the area chairs, and yes, because they did a great job. And the reviewers. Okay. So I'm going to name each of them. No, I'm just kidding. And of course, also our session chairs. A round of applause for them. And last but not least, to all of you, the 435 participants, thank you so much for coming.
Hi, hi from my side also. I will quickly squeeze between these amazing conference chairs to let you know that about 2 points that would be interesting for you maybe. There is some work still remaining related to MIDL Paris 2024. One is that a few of the papers will be invited for a special issue, which will be hosted by the Melba Journal. And you will probably get some email about that, some of you. And the other thing is that we are almost ready to publishing the proceedings, the final proceedings, which will be presented, will be published on the proceedings of machine learning research. We have some help from an amazing LaTeX whisperer among the board. I'm not going to name him, but he's helping a lot. We are almost ready to finalize the document, and you will receive some email in the following weeks in order to do a final proofreading of your paper. And then if we don't have any issues, we'll just proceed with publishing the proceedings. That's it. I will let Ninon give you some nice statistics and starts the awards.
Well, I'm not sure if the statistic is that nice, actually, because it's still in the category some mock work that could still be done. And for that, actually, we have to thank Attila Simko, who checks whether middle papers are reproducible, because if you check the web page here, there's some guidelines on how to make your paper reproducible, and different elements that Attila checked to see whether they were reproducible. And so the bad thing is that 30% of this year's repositories are completely empty. So you still have time to fix that. So please do so. But then there are also some good papers that are highlighted here. So that ticked vast majority of the boxes, of the reproducibility boxes. So congrats to these people. And now it's time for the awards. So it will start with the reviewers. So it's difficult to select 1 or 2 reviewers. So we have actually many outstanding reviewers. So who were not late to submit their reviews, which is very important when you organize a conference and you are chasing reviewers. So thank you for that. Of course, we corrected for the emergency reviewers that, of course, gave their reviews late because the others gave them late. And also reviewers that were engaged in really the discussion. This is an important part of MIDL, so we really wanted to put forward these outstanding reviewers. So here's a list of the outstanding reviewers, and the one that appear in red, they have this little highlight. These are non-faculty reviewers that we wanted to, again, put forward. So congrats to them all.
Okay, and now I think we can proceed with the awards that I think a lot of you are interested in. So first of all, we would like to thank a lot our award committees that during these 3 days we evaluated quite some papers, they saw a lot of posters, and they followed all the orals of all the orals of this year's conference. So thank you very much for all the work that you did during these 3 days. So the criteria for us to select or to convert to these papers were actually mainly 4: to have a presentation from the first authors of the papers. We were judging the quality of the original paper, the quality of the presentation, either in the oral or poster category, as well as its reproducibility, as Ninon also mentioned. So I think we can start with the first category, and we will start with the poster candidates. We were actually shortlisted 32 long papers. We did all this process only for the long papers this year. So this is the list with all the posters that they have been qualified to be candidates for the Best Poster Award. And after the committee passing from all of them, they converge on 5 different papers, which you can see here in the screen. And among these 5 papers, we are looking for 2, the runner-up poster award and the Best Poster Award. I hope the authors of the papers will be in the room, so please, in case you are in the room, please come in front to give you also the certificate. So I hope you are ready for the announcement of the first runner-up poster award. And the award goes to the paper Diffusion X-ray Image Denoising from Daniel Sanderson and colleagues. So Daniel, if you're here, please come. and we can take a photo. And then the best poster award goes to leveraging probabilistic segmentation models for improved glaucoma diagnosis, a clinical pipeline award from Anna Wondram and colleagues. And if somebody of the authors are here, please come. Yeah, I forgot to mention that the papers, they go with some prizes. One is for Paris and one is some money for this. Okay, and now I think we have converged to the orals, and this is actually the shortlisted orals. Yes, there is a typo here. Again, we have here shortlisted 12 long papers. You can see them in this slide here. Congratulations to all. You make the committee, the work of the committee very challenging. And from this, the first the runner-up best oral paper award goes to Accelerating Physics-Informed Neural Fields from Fast CT Perfusion Analysis in Acute Ischemic Stroke from Lucas De Vries. Please, Lucas, come. Thank you. Congratulations. And now, the time that all of you are waiting for, so we are going to announce the best oral paper award, which goes to SINR, Spine Enhanced Implicit Neural Representation for Multimodal Registration from Vasiliki Sideri Lamprecha and colleagues from Germany. Okay, thank you very much. And now I think we can continue, and we will give the floor to the board of MIDL for the rest of the announcements.
Thank you. I'm Gert Litjens on behalf of the MIDL board. I have some very short announcements. I know you want to get out of here, and some of you might want to watch the match at 6. But first off, I would like to thank the organizers again for an amazing conference. I thoroughly enjoyed myself, maybe a bit too much last night, but I think that holds for many of us. So maybe another round of applause for the local organizers. So I'll be brief. I will start with the fact that, of course, MIDL is a conference, you're here, but we also do a lot of other things throughout the year. So we have many online events, roughly 4 a year. Ranging from, we had a welcoming women workshop a couple months ago, reproducibility, but also scientific paper writing. So please follow the MIDL.io website to see all the other events that we organize. And with that, Alessa already talked about this during the opening. I will just do a brief recap. We're looking for a young researcher board, so PhDs and postdocs, to also make sure that the voices of the young researchers in the community are heard by the board. So if you want to sign up for that, please send a short CV by the end of August to juniorboard@middle.io. And also, if you have any questions about it, don't hesitate to email or approach us directly. And with that out of the way, I have one final exciting announcement, and that's where we're going next year. And for that, I would like to ask Tolga if he can come forward already. And if you know Tolga, you might already know where we are going. But next year, we're going to Salt Lake City, so back to the US. And I'll give the floor to Tolga to do the introduction.
Well, thank you. We're very excited to organize the next edition of MIDL in Salt Lake City. We hope to put together an exciting program for you, and we look forward to your paper submissions, and we are looking forward to welcoming you. More information will be soon available on the website, and we have a little video for you for the introduction. Thank you, and we look forward to welcoming you.
Okay, so I guess it's time for the really final word. But why am I alone here? I wasn't alone organizing, right? So come on, all of you. Okay.
Okay.
So we really need to finish because the computer said it will restart in 2 minutes. So I guess it's just like time to wish you like all a nice journey back, and it was really a pleasure to host you here. I hope that you enjoy the conference and that we will see you like next year. Anything else?
Yes, no. See you next year in US.
See you next year.
See you next year. Thank you. Bye.